My journey so far, I was born in this place. It's a very remote village in West Bengal, Midnapur state, about 21 kilometers exactly from IIT Kharagpur towards Kolkata. That's my house, and it's on the bank of a beautiful river called River Kamshavati, which separates the two towns, Midnapur town and Kharagpur town. And then this is my primary school where I used to go, class 1, class 2, class 3. Then this is where at Imperial College London that I work. In between, I went to Jadavpur University for my first degree in electrical. Then to GATE exam, I came to the University of Science. Today they are having their 50th reunion for the Alumni Association. So I have to go there in the afternoon. That's why I requested the chair to schedule my talk in the morning. So that's there. But my work is mainly the oscillations, a pathway to blackout. I work in electric power engineering. So the low frequency oscillations in large power system has always interested me. What is that? So you know that you keep on hearing about large power blackout in the electricity network. So there is a mechanism before the blackout happens. So the mechanism is there are lots of big synchronous generators in power plants. 500 megawatts, single unit, 600 megawatts, 400 megawatts, very common in a country like India. So what happens whenever there is some fault in a transmission line, lightning striking, so because of that fault, there will be an unbalance between the power that is being coming from the input side before electromechanical conversion and the power on the electrical side. So in that process, when you have large synchronous machines with large turbine dumping power, constant torque, so electrical power has dropped because of the fault, because that electrical power is function of the electrical voltage and other quantities. Fault actually drops the voltage, so power that would be produced electrically would drop. So now what happens? A process starts inside the large mass. You know, 600 megawatt turbines means it could be a couple of tens of tons, turbine, generators, excitation system. So then it starts actually accelerating because of this unbalance between the power. And then the fault is cleared. After the fault is cleared, the system is coming back to normalcy. How the fault is cleared by the circuit breaker, and maybe in 100 milliseconds or 120 milliseconds, the fault will get cleared up. Because the fault is normally temporary in nature. Lightning came, it struck the line, breaker opened, and lightning disappeared. The breaker again closed the line. So again, the electrical side is normal. So at that point, we still have some unbalanced amount of energy. So how that unbalanced amount of energy manifests amongst different generators, like northeastern side, so there are generators in Farakka, in West Bengal, 500 megawatt unit. Then you could also have 4 generating units, say here in Raichur district. So between northeast to this, so to this link, everything is connected. So when the system comes back to the next equilibrium point, there would always be some kind of low frequency oscillations. So these low frequency oscillations create bottleneck for the transfer capability of the line. And when that happens, many control and protection systems pick up wrongly, and then they disconnect the line, and then you don't have any power. So this is the blackout. All over the world, history of the blackout, everywhere this oscillations is a problem. So that interested me ever since I was a master student at University of Science. And then I worked on that. So essentially, I casted that problem as a linear reverse control problem. So this is the linear model of the plant. So this plant means all over the country, like you have one grid India, all thousands of generators, and there are things linearized and linear dynamical systems, and they are controlled. They are all multivariable, so they are all matrix. And how you design the control so that under different operating circumstances, different demand, different generation, different circuit strength, different topology, this control is robust so that the system remains synchronously connected and stable. So this is the mixed sensitivity and based formulation, this maths. So we do the H infinity based the solutions. I don't want to get into the detail of this. So how you solve that through analytical solution is always a point, but that's always an issue with the weight selections. So we went with the numerical solution, this solution in the space, tractable, frequency, and time domain objectives. So we could put all the oscillations essentially mathematically is an eigenvalue with real part which is very small and imaginary part which would be about 2 Hz. So this is the eigenplane, so we must put it here so that we have good damping. These lines are actually constant damping ratio lines. So we provide a 15% damping ratio, so the oscillations would dampen out quickly. So that system is back to normal in a synchronous mode. So this is another model network, Northeast US, that has become now IEEE 16 bus a test step that we developed for IEEE as a benchmark. And there we put some controller called thyristor control series capacitor. So this is for power transfer enhancement in transmission lines. There are many TCSC in this country. The first was actually in Kanpur Vallabhgad line in late 90s. Now there are many. So one of them is a power flow controller, and we design the control, and we are bringing in all the signals from remote locations, because oscillations may not be observable where your the controller is, or your actuator is. So then we do that. So then we come with some design, and then we test the robustness. You see that when the power flows across different corridors and it varies from 100 to 900 megawatt, we are getting actually good damping, more or less, very reliable damping. And when the demand also changes by its nature, sometimes we have constant power type of demand, lots of heavy electronics oriented loads are different characteristics, and heating loads are different characteristics. So if we combine the mixture of them, how the oscillations are damped out, that is this. And finally, the last one, you see that some of the lines are not in or out. So how at that point of time the system still remains stable. Then the issue was that we are getting the signals from different locations, so it needed time to get into the controller location. So there's a time delay. So that we handle with a method called unified Smith predictor. So normal, the problem with power network dynamic model, it has got some real poles, large negative real poles, and then also it has got complex conjugate pole very close to the imaginary axis. So these two, by prediction, is difficult to handle by a single method of prediction like classical Smith prediction or modified Smith prediction. So we put them together, and then we got a controller that we tested in real time at Imperial College. That was around 2004-05. Hardware in the loop with copolar simulators, and you could see that the damping. After that, I realized that those controller based on H infinity in control theory come with a large structure control. So how you make them smaller, low order, so that the vendor like ABB, Siemens, GE, they can develop a lower order control. So I did a lot of work on eigenvalue, distance minimization, robust pole placement, Kharitonov, many of you know Kharitonov based approach, sound stabilization. They are all in these two books. And the second one was more popular also in China. So there's a Chinese version of that. And then after that, there was this more integration of large wind farm. So then I took actually this dynamic modeling for low frequency study into asynchronous generation framework as well. So that is the wind farm. So putting two together, we had a unified modeling. And those modeling included voltage source converter and multimodular converters, power electronic side. and then we did some eigenvalue analysis.
Please summarize.
Yes, I'm doing this, just 2 slides. So this is typically, you see that one large wind farm, part of the wind farm, 500 megawatt. So how all those dynamics interact and do that along with the network. So this is how the nodes of different frequency now, 310 to 15 hertz and so on, typically at the HVDC converter side. So then I can simplify them by various methods, in linear system theory. We got good results. So finally, we came with, again on that, some estimations, techniques and so on, published a couple of books. So these challenges have been handled very well, and some of them have been taken up by various companies. And on the distribution part, the spectrum power of Siemens, that spectrum power has got state estimator and Boulevard controller that is now working in different country. So this is my researchers, and I have really worked with Rainrop here, who is also a fellow this year. Congratulations, Rainrop. His student was Abhinav. He and three of us have worked and wrote lots of paper together. Other students worked. So this is now my current group at Imperial, and I'm working in 4 areas. Those 4 books. I think that's it. And these are the people who funded me for my research in the last 25 years. I'm done.
Accurate rainfall prediction is one of the grand challenges in environmental research due to its relevance in understanding climate change and its accompanying social and economic impact. Professor Karl Salman, who is a Nobel laureate in physics in 2021, he relates the rainfall modeling with the climate change. So the question comes: is it too late to stop this climate change problem? According to me, I didn't know. There are 2 ways to handle the climate change issues. First, we should measure the rainfall and take preventive action for the society, and with a long-term goal to control the climate change. As far as the Indian tradition is concerned, Kautilya's Arthashastra, which was written in 3rd century BC, contains the record of scientific measurements of rainfall and its applications to the country's revenues and relief work. Kalidasa, who wrote Meghadutas in 4th to 5th century CE, also talks about cloud, but in a poetic fashion. In rainfall measurements, in rainfall, several factors such as temperature, humidity, aerosol, air current, secondary parameters such as arc topology influence the raindrop size distribution at different altitudes via complex microphysical processes such as coalescence, fragmentation, and phase change. This is an input parameter for Doppler weather radar that measures the rainfall rate using this formula, which is known as Marshall and Palmer formula. This relates the diameter of the droplet with the rainfall rate, and currently this is unknown. Just to take some few points over here, neglecting coalescence and breakup in the rainfall modeling can introduce 10 to 20% of error in the rainfall estimations. And this error could be significantly high if we include evaporation and airstream. Bigger raindrops are essentially non-spherical because surface tension will not be able to hold it. And raindrop size distribution, as I said, is unknown. The weather radar, what it does, it sends a signal and gets the reflectivity. This reflectivity which is get and that relates to the rainfall is essentially 6th power of the drop size diameter. And you think about it, a small error in fact may lead to a big measurements errors. So of course there are some people have recognized this issue and there are some direct measurements. This is an initiative taken by Indian government known as SciFex project. This is kind of multi-hundred crores project. They use research flight with lot of sensors in it, and they take this flight off during rain conditions, and they get the rainfall rate at different altitudes in the real rain conditions. This is a picture taken from the NASA website. This gives the drop size distribution across the cloud from the ground. The red region here are bigger droplets, green regions are tiny intermediate size droplets, and near the cloud you can see these blue regions which are small droplets. So of course, although the satellite data, some direct measurements are available, they are very limited, and most of the time they are not available. So researchers make assumption on the drop size distribution to measure the rainfall. So, in a nutshell, the issues in rainfall modeling currently, which is like by far from perfect, are accurate rainfall measurement requires drop size distribution in the bulk area region. And most of the measurements still today are done in the ground level or in the cloud level. No data or very limited satellite data are available. Largely influenced by temperature and humidity gradient, which are significant factors in Indian conditions. We have not only the temperature and humidity gradient in the vertical direction, we have also variation in the horizontal directions. When the raindrop starts to fall from the cloud, the temperature is below 0 degrees centigrade and it is super saturated. As they fall, the temperature increases and humidity decreases. So essentially, the falling raindrops will experience different conditions as they fall. So it is a very, very complex problem, and it is very important also in terms of rainfall measurements. So we established a raindrop research facility at IIT Hyderabad. It's a unique facility. It's nowhere across the globe. This is the first time we have established. This recreates the dynamic weather condition from the cloud to the ground, and thereby we can actually recreate the condition of any parts of our country. So I am not going to detail of this, but I will tell this has been built from scratch. I mean, this designing, fabrication, everything has been done from scratch. So this is the outer chiller unit, cooling unit, and there is a jet type vertical wind tunnel and vacuum pump. So we have dedicated this facility to Professor Narasimha. So just to tell you how it works, because the cloud height is, let's say, 6 to 7 kilometers. So in order to simulate all these things across the atmosphere, we have to build a tunnel of something like 6-7 kilometers, which is impossible. So what we do is we suspend the droplet by blowing the air in the upward direction, and we condition the air in such a way that the droplets which are suspended here get the local condition as if they are falling from the cloud. So we can actually, using this facility, we can vary the temperature from minus 10 degrees centigrade to 40 degrees centigrade. Relative humidity can be varied from 0 to 95%, and with a flow rate of 2000 meter cube per hour. You imagine the complexity. When you switch on the AC, let's say to 20 degree, it takes more than half an hour to get this feeling of 20 degree. You will not even get it. But here, the total travel time is few seconds. Within that, atmospheric air has to be conditioned to these desired conditions, and you get these droplets, and so the droplet can fill the local atmospheric conditions. So it is a very complex mechanical engineering, electrical engineering. Even this vacuum pump I have designed myself. So just to tell you the impact of the work, as you might have seen, when the raindrop falls, you always see kind of updrift because of the temperature gradient across the atmosphere. So there is an updrift, and this droplet will encounter this airstream. And I'm talking about only one phenomenon, which is fragmentation. Of course, we have coalescence and phase change, other things are happening. Just today, I am focusing on evaporations. So these are the typical Weber number which you observe in atmosphere. So the droplets undergoes different kind of fragmentation process, as you can see. But by doing this, it actually, what happens is, when the droplet encounters these airstreams, it flattens out because of the aerodynamic force. And then it bulges up to form a bag. Now this bag ruptures due to the pressure difference across the ring to form these tiny satellite droplets. Now, because of the surface tension, this film, the remaining film will attract towards the ring, and it fragments due to Rayleigh-Plateau capillary instability. All these theories we have done, and it can produce intermediate size of droplets. Finally, the nodes which are around this ring will fragment and it produce bigger size of droplets. You see, a simple bag fragmentation process, only one, can produce different size of droplets. Tiny satellite droplet, intermediate size of droplet, ligaments, and bigger droplets. So it is a very challenging thing to get this drop size distribution. Just to tell you, this article highlights published in Nature Physics says that a single drop fragmentation determines the size distribution of the raindrops. So this really is very motivating. But the challenge is, let's say, most of the time we do shadowgraphy, we take an image. So when you take an image, you get a planar view. You don't get the 3D informations. So we use holography. So what it does is, it sends I'm not going to the setup. Again, this has been established by ourselves only. We have not purchased from anywhere. So we use a coherent laser light, a green light, when you send it and you hit the droplet region, some part of the light will be reflected, whereas the remaining background will remain unscattered. This creates interference patterns which are known as fringes. This is a movie, I am not able to play it today. These fringes indicate the phase and amplitude information of the object, and the depth information of this object, in this case the droplets, are encoded in the fringe spacing of this recorded hologram. So you can see these fringes. So by studying this fringe spacing, you can get the depth information. So essentially, in a volume, how many different size of droplets are present, you can get it. And the second step is to reconstruct the volume to get the 3D shape and position of the droplet. Now, several of this image has to be processed, and along the depth also. So it is mechanically it is not possible. So we use a CNN-based machine learning technique to use for the sedimentation process and to get, so that we can get the droplet shape and the position of the droplets. I am not going to detail. If somebody is interested, you can talk about it after that. So this is the comparisons with the previous model. As I said, Balloon-Knox and Bosa has developed a model. There are several other models also. But all these models require this average drop size diameters as an input parameters, which is unknown. How do you know it a priori? So these are essentially input parameters, and most of the measurements are wrong in the varying atmospheric conditions. But here we saw a comparison of the normal size distribution of the droplets with the normalized diameters. Our model does not require it because we estimate it. We estimate using holography, so we know the average diameters of the droplets. So you can see that this is the theoretical. This is a direct measurement by Marshall and Palmer in a steady range conditions. This line, which is below this red line. Red line is our model, and the present experiments are these symbols. And this is the results by Balloon-Knox and Bosa. And you can clearly see that when the size of the droplets is bigger, it deviates significantly. Whereas our model, which does not require any input parameters, predict the rainfall very accurately. These are real measurement done by Marshall and Palmer in 1948.
Can you summarize them?
Yeah, 2 minutes, 1 minute. So this is a comparison with the in situ measurement. Remember, in the beginning of my talk, I talked about SciFX project. Our Indian government initiatives which measure the drop size distribution at different altitudes. So this is done in Bhubaneswar on this date, Bhubaneswar to Vijayawada flights, Vijayawada to Hyderabad flights. And you can see this has been summarized over here. X is again the normalized diameters. And you can see that our model is predicting this, whatever we observe, direct measurements of the rainfall, drop size distribution at different altitudes. Now, knowing the drop size distribution is not enough. But if you know it, what you can do is you can integrate. If you know the number of different size of droplet, you can integrate it like this to get the rainfall rate. And when we use it from our experiment, we found that the rainfall model in that particular conditions is derived like this. So you can see that this is D average is related with the rainfall. And this formula, if you see, it is very close to the Marshall and Palmer formula, which I showed in the beginning. So the take-home message from this talk is the study of clouds and raindrops is not only relevant but also very interesting. And actually, it reminds me today what Professor Ashutosh Sharma, I will end this thing by saying this. He said like lock and key problems. You have set up to and you keep identifying the different problems to solve it, or you identify a problem and try to find a key to solve it. So in this case, I found it. Thanks to Professor Narasimha who told me that this is a problem and nobody is working. So I tried to identify the real problem in 2013. It took me 11 years to establish this facility from scratch. So I actually went with I did not have a key, so I tried to find the key by myself. But this is the beginning. As I said, our atmosphere is very versatile. So this is just the beginning. We have to go for a region-specific rainfall model to predict the rainfall accurately in different parts of our country. Finally, I'd like to thank my students and collaborators and all the funding agencies who have supported me in this study. I'd like to thank you very much.
Good afternoon, everybody. It's a great pleasure for me and privilege to be presenting to this august audience. I also thank IME for the election to the fellowship and look forward to collaborating with many of you for various initiatives that I might have. Our work has been focused on thinking about healthcare systems and using engineering approaches to them. In the next 15 minutes or so, I thought I'll do three things. In one slide, try and present an overview of our work, and then talk to you about two problems. One is to think about the ways in which viral infections play out in a general enough manner that we can think about applying that framework for different types of viral infections. And then a very specific problem of trying to understand quantitatively what COVID-19 vaccine efficacies are, where they come from, and how they can be engineered. So here's a brief overview of our work. We look at the computational biology of infectious diseases. We focused over the years on several important infectious diseases, HIV, hepatitis C, TB, COVID. In the recent times, we've also done some work on microbiomes. Today, I won't talk about this in the interest of time. We have looked at problems in this space that occur at several length and time scales, starting from what happens at the cellular level, where pathogens hijack cellular replication machineries and make more copies of themselves, thus affecting normal physiology. We study these processes using ideas from reaction networks, dynamical systems, stochastic simulations, and so on. One scale larger, we look at what happens at the dynamics within hosts in terms of how these diseases progress and how interventions alter that progression. And this we analyze using notions for population dynamics, spatiotemporal analysis, drug pharmacokinetics, and pharmacodynamics. A step further, because of these interventions, we see pathogens evolving, and therefore we have to think over larger time scales where mutations and other evolutionary forces alter host-pathogen interactions. And we study these processes using ideas from population genetics, evolutionary theory, and immune responses. And lastly, when this happens, it alters epidemiology. So we're going to think also about what happens at the population scale. And here we think about modeling based on epidemics, like the SIR type models that we saw during the pandemic, but also more interestingly, nested models which tell us how forces at the population level influence evolution of the pathogens and then play back into what happens at the intracellular level. And many times these processes are not fully mechanistically described, and we take recourse there to ideas from statistical learning and AI. So with those brief remarks of the overall program that we are running in our lab, I'll switch to the first problem that I want to talk about, which is the outcomes of viral infection. Turns out this is a decades-old problem that virologists have been thinking about, although in the recent pandemic times it became extremely evident to us, because we saw people, some of them privileged ones, not seeing any symptoms of COVID, whereas others suffering severe pathogenesis and having been hospitalized and so on. Right from the 80s, people have thought about this problem. This problem has been best studied in this experimental system of mice infected with a virus called the lymphocytic poliomyelitis virus. And when you infect these mice with this virus, using different inoculum sizes, you can produce these outcomes that we see playing out in different viral infections experimentally. So for example, if you have low viral inoculum sizes, then what is shown here is the virus in the spleen of these mice, but a measure of how much pathogen there is in the body. These levels rise, and then with time they fall, and the virus is completely cleared. So this is an outcome that is typically called clearance. So you're free of the infection. Alternatively, if you have intermediate viral inoculum sizes, then you see trends that are similar, but here it turns out many mice actually die from what is called immunopathology. And what is shown here at the bottom is the histology of the spleen, and you can see here severe tissue damage, where this is more or less normal tissue. Interestingly, if you have high inoculum sizes, then the mice don't die, but the infection turns persistent. You don't clear the infection, you have long-lived persistence of the infection. So you're seeing these three infection outcomes playing out. And it turns out, if you look more closely at a whole host of viral infections and hosts, you see these very outcomes playing out to different extents. Very quickly, if you have HIV infection, for example, 100% of the time you see persistence. Measles, 100% of the time clearance. Hepatitis C, clearance 25% of the time, persistence on other occasions. Flu, some percentage of clearance, some percentage of mortality, but no persistence. And this percentage of clearance usually depends on the strain, the H5N1, H3N1, 1 and so on. Hepatitis B, in neonates, it causes persistence, but in adults, it's clear. This LCMV infection in mice, as I mentioned, if you have a particular strain of the virus called the Armstrong strain, then you get clearance. Whereas if you have another strain called the clone 13, then you see the inoculum size dependent outcomes that I showed you in the previous slide. With COVID, of course, everybody knows, 95% of the time you see clearance, small percentage mortality, and in the recent times we are discovering that there is an extremely tiny percentage of the infected individuals that see long-term persistence of the infection. So what determines these outcomes, and can they be controlled? This was the question. So after looking at the literature for a while, people have come up with a whole host of factors. This is just again a one-slide history of all of the things that people have identified, going from viral genetics, inoculum sizes, CD8 T cell responses, which I will talk about in the next slide, other arms of the immune system, post-genetic factors, and so on. So if you read the literature, it appears that this is a result, the outcomes, of a complex interplay of a whole host of factors which make it extremely difficult to comprehend the outcomes and then manipulate them. We thought about this a little harder and realized that in the end there are just these three outcomes. So there must be something central to this whole process that dictates what outcomes are realized. If you could put our finger on that pulse, we might be able to extract the underlying mechanisms. So when we looked at the literature more closely, in the interest of time, I won't be able to present the rationale. But it turns out we came up with this hypothesis, which is that there is an underlying dynamical motif made up of what we call essential interactions of these cells called CD8 T cells, which kill infected cells, and antigen, which are infected cells. And this dynamical motif determines all of these outcomes. And all of the other factors that I listed in the previous slide only influence these very outcomes indirectly. So this was the hypothesis. So we tested this by constructing that dynamical motif and looking at the outcomes that it predicts. This is the motif. There are these infected cells. Their numbers rise because they produce more viruses. Those viruses go and infect other cells, and this way this number grows. These cells are recognized by these CD8 T cells, and that recognition causes these cells to become activated. These activated cells, they in turn kill these infected cells. But then when you have a large number of these infected cells, it turns out that they can trigger through sustained stimulation what is called exhaustion of these very CD8 T cells. These cells don't die though, they are now no longer able to kill these infected cells as effectively. So these are the essential interactions that I talked about. So when you put together equations that describe these interactions and ask what states are realized, you come up with a phase portrait of this kind. What is shown here are these infected cells and these CD8 T cells. In this phase portrait, you have three stable states. There is one state which has very high populations of infected cells and low populations of these CD8 T cells. This is the state of persistence. This is the opposite state where you have low populations of infected cells and high populations of these effector cells. This is clearance. Interestingly, there is also this unstable state called the saddle, which it turns out, I'll show you, represents this immunopathology. There is a separatrix that divides this phase diagram into two parts representing the bases of attraction of these two stable steady states. So what exactly happens with this phase portrait? If you are on this side of the phase of this separatrix, then you have relatively high populations of these infected cells compared to these CD8 T cells. You go to persistence. If you are on this side, you have low levels of these infected cells, then these effector cells are good, they can clear the infection. If you are close to the separatrix, it turns out that both these processes, the effectors killing these infected cells and these infected cells causing exhaustion of these effector cells, they become balanced. Both these populations rise. The effector cells are not in adequate numbers to get rid of the infection. These numbers are not in adequate numbers to cause sufficient exhaustion of these cells. So these numbers rise, but then when they rise along the separatrix, you'll see the trajectories go execute large excursions along the separatrix. When that happens, you have a build-up of infected cells and these killing cells, because of which large-scale tissue damage happens. That causes immunopathology. So these three states that we have in this phase diagram, they underlie the three different outcomes that you see of all these viral infections. So, sorry? Okay. I'm taking too much time. All I'd say is this explains what happens in the experiments. You have low, medium, and high inoculum sizes, for example, on the x-axis. the fraction of mice that are persistently infected, the fraction that die, and you'll see as you go from the left to the right, low inoculum sizes, nobody dies, nobody is persistently infected. High inoculum sizes, everybody, nobody dies again, everybody is persistently infected, and somewhere in the middle you see death from immunopathology. So what is happening here is you are cutting across the separatrix like this. Here everybody is clear, people die, here everybody has persistent infections. So you begin to make sense of these experiments using this particular phase diagram. And we have shown by applying this to several other infections that you can describe what happens with post-treatment control of hepatitis C infections, what happens with HIV infections in monkey systems, macaque models, and with the different outcomes that we saw with COVID. You could describe all of those with this very framework. What's the advantage of constructing a framework like this? It gives us quantitative insights into the various interventions that people use for dealing with these infections, and also allows us to synthesize the way these infections work in this unified framework. So for example, our goal is to see if we can move the infection system from this part of the phase diagram to this. And there are many ways of doing that. For example, you could lower the number of infected cells, and you can show that all the drugs that we use, as well as what are called therapeutic antibody vaccines, do just that. You could increase the number of CD8 T cells, and there are T cell vaccines that are being developed that do that. You would like to increase the rate at which these cells get activated, and there are ways in which that is being accomplished through mechanisms that are called passive vaccination. You could reduce the exhaustion of CD8 T cells, and that's exactly what immunotherapy does, including for cancer therapies. And you could also increase the rate of killing by these CD8 T cells, and that's what treatments like CAR T cell therapies do. So you have now this entire gamut of treatments that you can understand by looking at this one particular phase diagram that we can construct. And what's the goal? We can quantify how much of these interventions are necessary for you to move from this side of the phase diagram to this. And the quantitative aspect here is not to drive the infection completely to clearance, but drive it to the region of the phase diagram where the body's immune system can take over. So you can optimize the amount of drugs that you can use. So I have another problem, but I'm going to stop in the interest of time. But this is the flavor with which our group has been thinking about these problems. I'll end by just showing you what we can do with these COVID vaccines. Here, the idea was that antibodies are being developed that vary from one individual to another. We quantified the landscape of the variations that these antibodies represent, and based on that, we could build simulations that represented virtual clinical trials that were conducted, manifestations of what was conducted during these COVID-19 vaccine development initiatives. And based on this, we started making predictions that were quantitative of the amount of protection that these vaccines could confer as a function of their dosages. And in this particular case, concentrations of the antibodies that these vaccines elicited in the blood. So this, each of these symbols here, this is my last slide, each of these symbols here represents the efficacies of the various vaccines that were all approved for clinical use, including the ones that we took. And this line is a prediction of our theory without any adjustable parameters. So we have a handle now in terms of describing quantitatively what these vaccines are able to do. And what's advantages of this, not only is the understanding that we get, but also that there's a predictive handle here. This is the concentration of these antibodies that are elicited by these vaccines in the blood of vaccinated individuals. Based on that, we can predict vaccine efficacies. What it means is that you don't need to do expensive phase 3 clinical trials. These numbers are obtained by looking at how many people are actually infected and don't manifest symptoms and so on. But here, you don't need to go through the infection process at all. You vaccinate individuals, draw antibodies, look at the levels that the antibodies represent, and make predictions. So while this may not be great for deciding whether a vaccine is really efficacious, it's very, very good for deciding whether a vaccine is or vaccine candidate is not efficacious. Because if it doesn't produce the right kinds of antibodies, you can rule it out. You don't have to take it to further development. So in this way, you expedite vaccine development initiatives. So with that, I want to stop. Not surprised. Thank colleagues who have been part of these efforts, sources of funding, and thank you all for your attention.
So this is one, I'm a chemical engineer, so I work on many problems, but this is one of the contemporary problems which currently many of us are working. Right. So let me focus on not what I have done mostly, but what exactly should be done to basically achieve this net zero. And before we basically talk about net zero, let me tell you the gravity of the problem, because I have seen in literature many a times this problem has been trivialized. And once you trivialize the problem, then you don't understand the gravity of the situation. So my challenge here would be to basically explain you the gravity of the situation so that it's easier for us to figure out where the solution should basically come from. So if you talk about this particular data, what is the most important data over here is this number here, 40 billion tons of carbon dioxide, which our population of roughly 8 billion.
Sorry to interrupt you, but it's just a question. Most of these people are aware of.
Yeah.
So although you seem to think that it's trivialization of the problem, I think people are aware. So can we focus on what you
Yes, I will do
what
that.
you are doing?
Yeah, that I will do. But I just want to introduce the problem so that it's easier for people to understand where the solutions would come from. So if you talk about these numbers, if you see per capita emission of CO2 is roughly 5,000 ton per year. That's a significantly large number, and if you look into these numbers, you will see that this 1.5 degree centigrade bus has already been missed. It basically means that in next 5-6 years we will be emitting this much already. So this is not a target one should be having at this point of time. This is the target one should be focusing on. And from there we see that there is a corridor of roughly 1,000 billion tons of carbon dioxide. And if you have to do something like that, then it basically means that 700 billion tons of carbon dioxide has to be reduced with this 2 degree scenario in next 25 years. Now this is the quantum which we'll have to basically focus on. 700 billion tons, obviously each of these industries will require a different solution. Easiest is to do with power. Industry is slightly difficult, transport is going to be also difficult. But what exactly is the message in this particular slide is that there are three major ways. One is reduced consumption, which basically contradicts our aspirational goal as well as the GDP growth. So obviously I'm not going to talk about it. The two other solutions are going to be renewables, which has its own problem. I don't want to talk about it. But the other solution, which is that the emissions which we have has to be captured and sequestered or captured and utilized. So when you talk about this is what is carbon dioxide capture, utilization, sequestration people talk about, and every time you will hear that we work in this particular topic. You see here, if I have to capture carbon dioxide, either you capture it from here, that is the point source, or you capture it from here, which is directly from the air. If you are going to capture it from here, there are two challenges, which is one is obviously thermodynamics has to be taken care. The thermodynamics of the process here basically means I have to separate one carbon dioxide molecule from the 10 other molecules, and for simplicity we can assume it to be nitrogen. So the thermodynamics over here is that one molecule has to be separated from 10 other nitrogen molecules. And the kinetics, which I will talk about later in the slide. So here the kinetics is a bigger challenge. This is thermodynamics is not a big challenge. Over here, kinetics is not a problem. I can basically put a unit and it can slowly do its work because it's directly capturing CO2 from the air. But here the thermodynamics is really big challenge. Here the separation is going to happen between one molecule of CO2 surrounded by 2500 molecules of nitrogen. Okay, now this is a very big challenge thermodynamically. If you are going to separate one molecule of CO2 from 2500 molecules of nitrogen, the amount of energy which you are going to pump in requires a very different kind of solution. So I am not going to talk in detail, but the challenges which I was trying to tell you is there very clearly. And in this particular case, one has to always remember that we are talking about net zero. What exactly net zero mean? The net zero means that the one molecule of CO2 which I am capturing from here, or one molecule of CO2 which I am capturing from here, either I am going to utilize it, or when I am going to put it under the earth, in this entire process of capture, transportation, sequestration, or capture and utilization, I should be emitting less than one molecule of CO2. This is a challenge. It's not a challenge of cost. It's a challenge of achieving net zero. If I am capturing one molecule of CO2 and in the process of processing it, if I am emitting more than one molecule of CO2, then my purpose is not served. So this is the challenge which I am sure people should be focusing on. And on this I will try to tell you the biggest solution which people talk about currently is some of these amine solvents. And one such amine solvent which is commercially available is called CanSol, which is a proprietary solvent given by Shell. And most of the units, technique or any other institution which will basically give you a solution of carbon dioxide capture will mostly depend on this solvent. Now let's look at the number. The number says that for capturing 1 ton of carbon dioxide, you are going to consume 2 gigajoule of energy. 1 ton capture of carbon dioxide, this capture process will consume 2 gigajoule of energy. So the obvious question is that where this 2 gigajoule of energy will come from? This 2 gigajoule of energy comes from production of this 1000 kilogram of carbon dioxide. You are basically producing 1000 kilowatt hour of electricity. 1 unit produces 1 kg of CO2 roughly. So what does this mean? I am producing 1000 kilowatt hour of electricity, and because of that I am also emitting 1000 kilogram of CO2, and to capture this CO2 I have to consume 2 gigajoule of energy as per the current process. So what is the value of 1000 kilowatt of electricity? Is 3.6 gigajoule. 1 hour will be 3600 seconds, 1000 watt will become 1000 into 1000 watt. So that basically means if I have been producing 3.6 gigajoule of energy, and out of that if I am consuming 2 gigajoule just for capturing it, what is the energy penalty we are talking about? More than 60% what I have produced will get consumed in CO2 capture. So that basically means that the process whichever we have to develop should not be taking this 2 gigajoule energy from somewhere else. It should be taking from the waste heat, and this is where the process has to fit. So most of the researchers typically don't really focus over here that this is the only energy which is available to you, and out of this 2 gigajoule if I can get even 1.5 gigajoule over here, then this particular process will have an energy penalty which is going to be close to 20-25%, which will make it commercially viable, as well it can make it net CO2 neutral. I don't want to talk about it over here, but the major challenge comes from this particular slide, and this is where the kinetics comes into picture. If I am going to focus on a point source capture, the challenge is profound. Let me tell you the example. In India, we have only one pilot plant in Vindhyachal Super Thermal Power Project, which is in Madhya Pradesh, where we have a pilot plant of 2 tons per day capture capacity. Now this is a pilot plant which is being celebrated, but let's try to understand what is the real requirement. This same power plant which we talk about, Vindhyachal Super Thermal Power Project, produces roughly 2500 megawatt of electricity. They have probably 500 units into 5 plus some 200 units as well. So let's try to look at, if I have a 500 megawatt capacity plant, how much CO2 will ultimately has to be processed per hour per second per day. Okay, so if you look into the data, a 500 megawatt power plant will emit 500 tons of carbon dioxide per hour. That basically converts into 0.15 tons of carbon dioxide per second. And if I am going to use that, there are going to be 8-9 molecules of nitrogen there. So the flue gas amount is roughly 96,000 tons per day from 1 unit of 500 megawatt plant. Okay, so let's try to see what do we have right now. The whatever molecules which we currently have, this is point, actually by mistake I have deleted it. So it's 0.2 to 0.25 gram of CO2 per gram of material is what is currently you will find in literature. That if I am going to produce a material which is going to capture CO2 from this flue gas, it will only capture 0.2 to 0.25 gram of carbon dioxide. So if you do a simple math from, this is the data which does not have any kinetics, so you will look for data which has some kinetics, that is per second, because this can be done in a day, in a half a day, in an hour. So if you look for a data which has some kinetics information, you see this is the data you get from the literature. Maximum you can do 0.009 gram of carbon dioxide per gram of material per second. So now what do we have? We need to basically convert this, capture this much from a 500 megawatt plant. So that basically tells you that I need roughly 16 tons of this material to capture from 500 megawatt power plant. Now since we have converted gram to tons, your kinetics will go down, your thermodynamics will go down, and for simplicity I have just assumed that let it go down just by half. So that basically means you will be needing 32 tons of this material, which will capture only 50% of the CO2 coming out because the kinetics has gone down to 2 seconds. So 32 tons of this material, there are two problems over here. How do you pack 32 tons of this material? If I have to pack 32 tons of this material in a reactor, my reactor will become 32 meter by 32 meter by 32 meter. This is a challenge of capacity, thermodynamics. If I am not able to increase the capacity per second, it is going to be really challenging. The second problem which you will see over here, now let's try to focus on the net CO2 zero. See, if you are going to produce 1 kilogram of steel, today in India we produce 1 kilogram of steel, and in the process 2.5 kilogram of carbon dioxide gets produced. If I am going to produce 1 kilogram of hydrogen, in the process 15 kilogram of carbon dioxide basically gets produced. Some of the material which is currently being proposed to be capturing carbon dioxide, one such material could be a metal organic framework. 1 kg of metal organic framework produces 2500 kilogram of carbon dioxide. This is the data from literature. Now let's look into this particular data. I need 32 tons of this material. Okay, and this is the rate at which we need to, this is the capture capacity of this particular material. So if I am going to produce 1 kilogram of metal organic framework, it basically means it will have 2500 kilogram of carbon dioxide. And since the ratio here is 1:4, it basically means this metal organic framework should be able to recycle for at least 10,000 times to capture its own carbon dioxide. Forget about the carbon dioxide which is going to capture from a power plant. So now if you are going to look for literature, where are those such material which captures 10,000 times? There are no metal organic framework which currently can be recycled for 10,000 times. So that basically tells you this is where the problem lies. You need to focus on the recyclability of the material rather than on the increasing the capture capacity of this particular material. Do I have some more time?
I think
No, I don't have, then we will move on. I'll talk about one important point though, which is from the economics point of view. These are some of the other problems which I don't want to talk about. The second solution which many times which is given, that why we are worried about all of these, we will capture the CO2, we will convert it into some product and it will become a circle, so we will be able to sustain. So let's try to understand where is the problem. Many a times you will see in literature that, oh, we don't have a good utilization process. Actually that's not the problem. We have many such processes which can utilize carbon dioxide. Urea is one such example. Okay, urea is basically a CO2 utilization process. But where the challenges lie? You see, if you are talking about urea production, thermodynamically you need 25 gigajoule of energy for per ton of urea production. In last 100 years of development by different catalysts, we have brought it down to 12.5. But still 12.5 gigajoule of energy is being consumed for urea production. If I am going to add 2 gigajoule per ton over here, where is the problem? 12.5 anyway I am doing, I will add another 2. So it's not a challenge from technical point of view, it's not a challenge. Where is the challenge? The challenge is how do we do this 12.5 gigajoule without producing carbon dioxide? Where is the other challenge? The challenge is, if you look into the data, a point source capture of carbon dioxide happens at $50 per ton. A direct air capture of carbon dioxide happens at $500 per ton. So if you convert $50 per ton, it basically means the carbon dioxide costs you 5 rupees a kg. Now what is the carbon percentage? What will you utilize in it? You will utilize the carbon part of CO2. What is the carbon percent? 25% in CO2 molecular weight wise if you look at it. So it basically means the cost of carbon is 20 rupees per kg for the CO2. What is the cost of carbon today in market? Coal India Limited produces 1 billion tons of coal every year. And 90% of it is sold at 1 rupees per kg. If you are going to assume 50% as in there or inorganics in there, the cost of carbon is 2 rupees. Now you are saying that I will produce this molecule of ethanol, methanol and all from the CO2 which I am going to capture from the air. What is the cost of carbon? 20 rupees per kg. Now what you are going to do with this? You will have to add hydrogen into it, which is currently at least 500, let's say even if it is 400 rupees per kg, and if you are going to produce methanol out of it, the raw material cost is 20 rupees per carbon, 50 rupees hydrogen, and then you will have to add the process cost. So what will be the cost of the methanol which you will produce from here? Minimum cost you will be able to produce it at 75 rupees per kg, which is 3 times more than currently available methanol. This is where the challenges are. If I am going to propose that I will capture CO2 directly from there and convert it into methanol, the cost is almost skyrocketed. So you can't really basically do this unless and until you figure out.
I request you to come out to what is your solution or what you are proposing and then some.
Solutions, obviously while I was talking I have already given the solutions. So solutions are focusing, you have to focus on problems where you will be able to reduce the CO2 footprint One of the problem solution could be that my material should be able to get recycled 1 million times, so that my CO2 footprint comes down. One of the solution could be that the process which I am going to basically propose will happen at a very low temperature of 60 degrees, 50 degrees of capture, 80 degrees or 90 degrees of regeneration, so that most of my waste energy is going to produce, get consumed for that 2 gigajoule requirement. These are the technical solutions. Obviously, the material has to be now researched better, so that my kinetics of the material improves, the recyclability of the material improves, and the integration with the process actually improves. So all of these we are doing in the lab. We have at least 5 such processes which can run between 6 degrees to 100 degrees, and we have been basically, this is on a direct air capture unit, this is Gen 2. Almost 200 such units are already being implemented, and we are already working on Gen 3. So the solution will be there, but we'll have to ask the right question. That's all I am going to talk about today. With that, I am going to end.
So, because everybody associates TCS here with IT and consulting, I thought it is better to start with where really there's a lot of work which people don't know. TCS does work with many other industries, not just doing IT and software development only. We work with life sciences, energy, resources, materials, healthcare. And we do work, have research going on across all these areas. Incidentally, Tata Research Development Research Center, popularly known as TRDC, was the first R&D center set up by TCS back in 1981. And the first research group that was set up, that will process engineering. The first director of TRDC was Prof Rajnish Kumar, who was incidentally a material scientist. So now I lead what is now called the engineering sciences, which is relatively broad in our goals and objectives plans. But some of this work is kind of a little bit more of open-ended and active. On the other hand, things that mature here will convert into what we call the programs. And one such program is digital twins, which what I have been kind of working with different industries for several years now. And we will spend more on this today in the next 10 minutes or so. So engineering sciences, we focus quite a lot on materials. We said starting with, of course, steel, minerals, metals, chemicals, things. And with the kind of industry that we are working with, we want to tell you what sustainability is an important problem. We have been working on various aspects related to sustainability, reducing emissions, improving resource utilization, improving energy efficiency, things like that, but most recently on batteries, carbon capture, and these are some of the research areas. But materials have a lot to play in our Narendra talked about drugs, etc. So some of the work is also on materials, still pharmaceutical players on and I think across all of them is actually what I have been trying to push through what earlier we used to model simulation optimization. Usually through what mostly people do, physics-based modeling, but so happens that because TCS works with all these industries and we get to work with industrial plants, we have to deal with data. Before data science and AI became buzzword, we had to deal with data. And there were times when I had to work on huge bits of logbooks, right, handwritten things, capture data from there to do simulations and help the plants in developing solutions. So I'm going to talk more on this one rather than that sort of things. We have been fortunate, I would say, to work on the entire materials value chain, starting from materials discovery to the finally circularity. Various aspects, both physics-based modeling, because as you all appreciate, the kind of systems that we work on, you have to obey the laws of physics. It's not like doing predictions on retail, doing predictions on what that matters, how people behave and things like that. Materials behave. Fortunately, certain physical laws are there, and then whatever hi-fi deep learning algorithm you may have, but it has to ultimately obey the physics of whatever system that you are modeling. I am going to talk more on the manufacturing. This is one of the problems that things that are already happening where we have to address them. While we do work on other problems of environmental materials. So one such thing across all of the digital twins, artificial intelligence solution that people have been working on. The concept that has really caught on is what is now called digital twins. This is how, while digital twin became a buzzword now, it was originally coined back in 2002 by instantly for manufacturing systems only. But it so happened that, as I said, because we were working with plants and we had to find solutions. I didn't know, like I said, I put artificial intelligence there because to attract people here. But as Shakespeare said, rose is rose. So we were not calling it a digital twin at that time, but we were actually developing and deploying such digital solutions earlier. This is the definition I give for a digital twin. You can read it yourself, I don't have to tell. But the emphasis is on this point, real time. Just want to emphasize that digital twin is not some machine learning model or a physics-based model or a control system or a simulator that's sitting in our laptops. Digital twin is a system first of all. It is not a model, it is not an algorithm alone. It's a system that has to work in real time with your actual physical system. I'm going to tell you how actually it works to ultimately help you in taking decisions to improve your KPIs. These KPIs could be plant health, plant productivity, or safety sometimes. Right? One of the challenging problems we have to deal with even safety. So this is the area where I have been, our team has been working on. Fortunately, had to work with actual real working plants and then develop solutions. But it's not actually easy. As I said, it's not just building some machine learning model or building a physics-based model or simulator. As when you are working with real plants, the first problem is actually the most challenging, quality of the data itself. Okay, when these models, every time you say I have a very high deep learning model, transformer model, but you will know that just like the climate, in fact climate is probably much better than these models. The model that works today may not work in the afternoon. How do you deal with it? Third is scale up. If that algorithm works for a particular plant, how can I actually do it for 100 such plants? Every time the same thing that worked for the same reactor will not work for the same reactor, same plant itself. The other thing is, many times people think the model is predictable, that you do simulations, help plot, etc. But when you actually go to the plant, they are not looking at just for only simulation or only prediction. They are actually looking for solutions. That my raw material quality has changed. How do I deal with product quality? How do I deal with emissions? How do I deal with product quality? So that is where automation comes in picture, and there is a lot of knowledge also has to be built in, not just only model. And finally, as I mentioned in the beginning, these things have to also obey physics. And this is where, in fact, one of the earliest things that we started what we call hybrid digital twins. So we have been working on how to address these challenges. So I will first start with the last point. This is the fundamental driver for these things, just manufacturing systems. Is to create a solution where you can combine physics, data science, domain knowledge, and as you would all appreciate, proof of the pudding is in the eating. So you have to test it. So no model is of any use unless it is actually tested with real data and then made to work and show that it is actually predicting and giving solutions that you can actually realize in real life. And that is how you build such solutions. And then do whatever is required. Like what Professor Sharma was saying, that you will have tools all over the place. But you need to bring all this together to bring that solution. The second, that is the first we address, that how do I bring in and take these hybrid systems, combining physics with AI, ML, whatever you may call. The second important thing is the first four problems. Now, those problems cannot be solved by only physics or data science. You have to actually deal with many things. It's actually a very, very complex problem, starting from raw data to all the way to the coming up with solutions. So, and that cannot be done actually, to tell you frankly, humanly. If you have to build a model for a plant, let's say boiler, blast furnace, or a distillation column, in the real plant, there are thousands of variables. For each variable, you have a model. And to build one model, to start from raw data, it just takes huge amount of time. Now just imagine you have to build hundreds of models. Take the raw data, clean it, build, identify factors, build models, then optimization. This actually takes quite a lot of time. So this is where we decided that it will not It is not possible to do remotely, that is to do platforms. That is when we created the platform of LinkedIn to do all these industrial analytics, starting from raw sensor data, lab data, or whatever management data, and take all the way to the prescriptive analytics. This is very, very generic, although it has been used later, but it can be used to do analytics of the historical data, because ultimately you have first prove whatever you are building has to actually show that it actually work with past data, and then take it online. So this here could be like gigabytes or terabytes of data, use this data to build models, and then push these models algorithms online, where you are simulating real-time streaming data coming at every second, thousands of parameters, and then you can customize it for any particular solution. In fact, we have started this especially for steel plants, then power plants, and currently we are now trying to take them to pharma and batteries. Like I said, long before digital twins and AI became very popular, we had actually one of the first digital twins we deployed for sponge iron plant. We deployed for one of our group companies, then pellet plants, especially for SR steel in India, Brazil, other things. But the real, this is about 20 years back. But the real breakthrough actually happened 10 years back, 2016, like 9 years. When this is another advantage of being working with TCS. That whatever we learned in steel plants, these people, when we get to work, we discuss with various other industries. So people from Japan, we were discussing with all these companies. They said, can you actually use this for reducing the commissioning time of boilers? And we are setting up boiler and not boilers, which is in fact like three equipment in a power plant, thermal power plant. So they were setting up ultra supercritical thermal power plant in Taiwan. So they said, can you use these all your algorithms to reduce the commissioning time? Even if you reduce by 1 day, it will save at least minimum $1.5 to $2 million. The challenge there is, in fact, the previous speaker spoke about carbon emissions. How to minimize emissions? They have to meet the WHO regulations. But at the same time, they have to have maximum efficiency. In fact, Japanese companies trade themselves saying that our efficiency is more than 90%. But you still have to, can we improve it? And then safety. So incidentally, the same Taiwan power plant, the previous, during commissioning itself, one of the boilers actually, there was explosion. So can you avoid when you are doing this? So fortunately, so this is how actually it works. You have the real plant here, you connect it to your communication channels, and you have the digital system here with various modules. Taking real-time data as well as historical data, to processing, integrating this data from various plants, starting from coal to steel. I'm just using substance as a generic term, but these are all essentially all models representing various variables like flow rates, temperatures, pressures, concentrations, etc. And then do online automation. So these outcomes are concepts and all of this happens in real time. Okay. Then we were fortunate to reduce NOx emissions. Incidentally, we reduced that commissioning time by 2 days. And then that one was set up. It has been running for the last 10 years in several power plants in Japan. Not only power plants, in fact, it's taken for other smaller boilers in different industries.
You have to summarize.
Yes, I'm good. In the interest of time, I'm not going to talk more about this, but I thought I'll spend some time on the steel plant example. In just 1 minute, there is a plant called Center plant, anyone who visited Center steel plants. This is actually the feed to the blast furnace, which produces hot metal or liquid iron, which is then refined to produce steel. The problem is, the raw material keeps changing, quality. We do not have any visibility into the actual manufacturing operation, you can only measure certain parameters. In fact, this particular equipment is a very complex multi-phase reactor. It moves like a train. So you cannot even put sensors. And then the product quality, it comes after 4 hours after the product is produced. And here this plant is producing 500 tons per hour. So in case the product quality does not meet, all of this has to be recycled. And sometimes the recycle rates are as high as 30%. So that means 30% of the capacity is actually lost. So we created a hybrid digital twin of the system, having a population validation, a 2D CFD model for this reactor, and then combine them with machine learning to finally do plant-wide optimization to that. Okay, this was deployed. This is similar to what I explained for the power plant, or more or less similar way. This was deployed in a couple of plants in India and a plant in UK. And that's why I want to spend time here. But where there is all, this is all already done and kind of demonstrated, where we are doing today. So a lot of this hybridization we did. So machine learning models work separately, physics models work separately, and then bring them together. Now we are doing what is called scientific machine learning, where we are combining neural nets and all the partial differential equations etc. together, so that you can actually get these things in real time. So if I am trying to simulate a blast furnace at distillation program, I can set up a neural network as well as solve all the equations together and just produce this. So you can know all temperatures, flow rates, pressures, etc. each and every location in the equipment or complete plant. And there is a lot of work we have done in heat exchangers. Yeah, this one more. The second one is generative AI. So if you people who are working on AI materials, there is a lot of work on discovery of materials. Okay, and they just talked about the manufacture. But there is a gap here. And the gap is how do you actually process development. So this is where actually now we are this paper was presented just last week at one of the top AI conferences for Units by one of my team members. Given the all knowledge of how these materials are produced, can we now use GenAI as well as of course physics simulations to come up with, let's say I want to produce ammonia. What is the flow sheet? What is the control system that to produce it? Okay. These first examples of some such things using these systems. Second one, yeah, so these are now kind of to summarize using physics-based machine learning and GenAI starting from material discovery to all the way to the circularity. Now we are trying to take them to some of these things like we talked about biopharma manufacturers. We have been collaborating tightly in deploying digital twins. In fact, one of those preliminary things we are actually planning to do. A couple of other things here, sustainable batteries and carbon capture instantly. So I will stop here.
So this is the outline of my lecture. I will talk about the nuclear phase. It is mostly for the nuclear industry. So I think many of you may not be aware of these activities which is taking part in the nuclear industry. So some of these things I will be highlighting here. Next, the green separations. And there are some of the challenging areas in the nuclear energy that I talk, and then also will be green solvent. I will be talking about the room temperature and liquids. So my green part of this lecture is one is the green separation. The chemicals which are used there are green. That means you do not have the carbon emitting or the something like the which you cannot really incinerate. So you generally get some amount of waste after every process. That process which is radioactive elements are used. So it is a problem of disposal. So they should be actually you can incinerate and they just they are not used. Number one. Number two will be a green process. So I will be going for a membrane-based separation process which has been developed indigenously at DARC. First time we have done this, and then third one is the green solvent. That is the room temperature ionic liquids, which you must be aware. These are the green solvents. This is a flow sheet of this nuclear fuel cycle. So we have this milling and mining first to start at the uranium wherever mines are there. From that it is converted to the oxide, then to the fuel, goes to the reactor, and after it it is used for a certain amount of time. The nuclear power is generated, and after that it is reprocessed. This is where we get the whatever unused uranium is there, and also whatever plutonium which is formed during this nuclear reaction. And then this recovered uranium is again cycled this way, and plutonium is going again for the conversion to the fast reactor project, which is there at our ICAR. And then after this reprocessing, we are having some of these radioactive waste which are generated. We call it as the byproducts for use in medicine, agriculture, or industries. Some of these are highly radioactive elements which are actually separated, and the other part of this radioactive waste is going to the waste storage and finally to the geological repositories where it will be left for disposal. So the objective is that whatever from this radioactive waste we are getting some of these radionuclides so that it can be used. So for that we have to develop some of the processes. Some of these three things we are telling. One is the actinides, that is for reducing the long-term hazards of this radioactive waste. Some of these are very, very long-lived, 10 to the power 6 years. So if you have this radioactive waste, where you are going to dispose? That is the major issue. So some of these actinides, long-lived actinides can be separated, that is number one goal. Then some of these high dose giving radionuclides like cesium-137 and strontium-90, which is a radionuclide, can have a lot of pharmaceutical use. So these three I will be discussing in this particular lecture. So now what you need actually for your have the radioactive waste, you know there are a lot of restrictions, you cannot just like that deal with those radionuclides, you need a lot of protection for that. And what you wish actually is a dream solvent where you have put it into the where a lot of elements are there, radioactive and non-radioactive. Out of that you have an organic solvent which can take out whatever you want. So that I call as a dream solvent. So people have been working all over the world, including the United States, China, Japan, and also European Union. There are a lot of projects for the radioactive waste. They are developing the reagents or the ligands, what you call, and they have carried out a lot of studies, including the hot runs, where you have taken the radioactive actual fields they have been taking, and those studies have been carried out. So I will not discuss about what are the a lot of research has been carried out. Just the final four, whatever people have zeroed down. One is a phosphine oxide, carbonyl methyl phosphine oxide, then there is a malonamide. This is again the Chinese people have gone for this TRPO, trialkyl phosphine oxide, and these are Japanese people, they have carried out studies with the DZA, that's a diglycolamide. So these two which are marked in green, they are the green solvents because there is no phosphorus here. In these two reagents, they have phosphorus. So when you cannot burn them, you ultimately have the phosphorus oxides. So that is the problem with these things. So we have carried out studies. Mostly European Union is focusing also to these two reagents, which are again green reagents. I'll just give a comparison of this. When you are using these reagents, this DZA particular molecule gives a maximum extraction when you carry out from a feed containing nitric acid, which generally all these nuclear fuel cycle feeds are in nitric acid, coincidentally. So that is why all these studies are in nitric acid medium. And you find that this DZA molecule, TODZA, it is the best. So what we carried out in our laboratory that we have developed a process for this, taking this DZA molecule, TODZA, and we have developed a solvent which was very, very efficient. We need the extraction of this long-lived actinides like americium-241, and that was separated in 3 stages and split in 4 stages. Very, very efficient solvent. The decontamination factors from the other existing metal ions in this radioactive waste were greater than 1000. So this was a very, very good result, but the problem was that you have a lot of volatile organic carbon which is used in this process because you are basically dealing with the solvent extraction process. So how you deal with that? So we thought we go for this membrane-based methods where you can have the supported liquid membrane, wherein the polymer flat sheets you take and then you put in the pores actually this organic solvent, and then because the volume inventory has decreased drastically. So there also the similar thing can be done. So we go to the liquid membrane studies, and as I already said that this is solid extraction has major problems like third phase formation, phase disengagement, time issues, phase entrainment, and large solvent inventory, which is leading to large amount of secondary waste, and also there are risks due to the inflammability of the solvent, and also you have to also deal with the volatile organic carbon. You go for the membrane, you have this low ligand inventory, and you can design the ligands which are the very high selectivity. That is major advantage which you can do. So if you have very, very expensive extractants also, you can go for that if you are going for the membrane-based separation method. So there are 2 types of configurations. There are many configurations available. We have gone for these 2. We have a very simplified picture I have given here, where you have 2 compartments. One is the source phase, another is the receiver phase. In between you have a membrane, flat sheet membrane. And in the pores you embed the ligand molecules which are in the carrier solvent, and the metal can be ferried from here to there, and the ligand comes back, and that is how the transport takes place, which time you get the complete transport of the metal ions. Now the second one is configuration is this, which is a hollow fiber supported liquid membrane, where you can really have the option of scalability and sustainability. So these are the 2 things which we have used in our laboratory. Now here I talk about this flat sheet with the first configuration, where you take the pure radioactive tracer. You find that it is taking much less time, less than an hour, and in presence of this 1 gram of when you have metal and loading, then it takes much longer time, around 50 hours or more is required. So if you go for this thing, and here I have shown it, if you take we have carried out most of these studies with simulated conditions, simulated high level waste, this actual nuclear waste we have simulated in the laboratory, and we have carried out the studies. also with the rare earth loadings. And here also you takes a lot of time in carrying out this transport studies. So the solution is that because this is very slow, it is not very feasible. So we go for the hollow fiber supported liquid membranes where the mass transfer rates are very fast. This is also this hollow fiber supported liquid membrane system where you have thousands of fibers are stacked into this hollow fiber cartridge, and you see this two view, the side view of the lumen, you have these pores in which this carrier solvent with the extractants can be there, or you have this top view of the lumen and you have this, these are again the pores in which this ligand can be there. And I have taken this particular example where this TODGA extractant was there, and you see this is does a very good mass transfer is there compared to the other extractants like this dimethyl dibutyl tetradecyl malonamide, which is this European Union people are working heavily, and also the CMPO, which is a phosphine oxide working at the American laboratories. So this one particularly has shown a much higher mass transfer rates. So what we did is we tried to scale it up in a hollow fiber setup, and we have taken in this case I think around 20 liter scale solution we have taken, and this has mass transfer rates for that come down. Even we have taken around lot of neodymium loading we have taken. Neodymium again taken as a simulant for the americium. Americium you cannot afford, a lot of dose will be there. So we have taken in the laboratory neodymium, which is a simulated form of this americium. And then the study it has shown that around 18 hours required for this transport of the neodymium from this field to the strip site. This also we have tried to bring down the volume. Again, this part we had from 20 liters in the receiver phase to 5 liters, and we found a lot of acid transporter because this was feed was containing 3 molar nitric acid. So in this case, we are spiking the intermittently with sodium hydroxide, and we also got similar type of mass transfer. It has been subsequently done at 50 liter scale. So this is what in the laboratory can be done, and this is the technology is available to be actually applied for the nuclear based processing. Yeah. Now I have this another for cesium. Again, this is 2 extractants which are there. One is a calyx crown and another is a dicarbonate. From this calyx crown we have taken, and we have seen the hollow fiber supported liquid membrane studies we have carried out, and it is shown that you can get nearly more than 90% can be transported. And similarly for the strontium 90, which is the application in the radiopharmaceuticals from the decay product yttrium 90. So this is the actually Argonne National Laboratory in the United States. They have developed this particular crown ether based solvent, which is very selective for the strontium 90. And these studies were carried out in our laboratory. Again, for the solvent extraction studies were carried out. It was very tedious to get a quantitative extraction. So we had to play around with this, diluent modification was required to get the proper diluent. And subsequently, we have seen that if you take this diluent mixture, that the quantitative transport was there, but subsequently there were a lot of this acid transport which was really affecting this strontium transport, and it is not very good. So in that case, we have tried to take out another solvent, which is the dodecane and nitrophenyl octyl ether based transport, which has carried out at a large scale in a hollow fiber supported liquid membrane, which has given around 90% transport in around 3 hours of time. So I'll quickly take it 1 or 2 minutes just into the room temperature ionic liquid. This is, I don't need to explain. These are very fancy things where it is called as a green solvent. They have shown a very high extraction compared to the normal solvent extraction with the molecular diluents. You see, this is 0.1 molar, ligand taken, 0.01 molar in case of this ionic liquid, 10 times less, but you see the extraction is even more than 10 times higher in case of the ionic liquids. This is the solvent extraction studies. But then solvent extraction again we wanted to avoid it. So we have gone for this, room temperature ionic liquid, how we can use it. This is a recent process called the pyrochemical reprocessing of the spent nuclear fuel, which is used for the Gen 4 reactors, particularly for the metallic fuels. So the advantage in this case is that no cooling of the spent nuclear fuel is required. It doesn't need the carbon hydrogen based solvents. Possibility of on-site reprocessing at the reactor site and can address a lot of non-proliferation issues. And this major problem in this case of the metallic fuel processing by the pyrochemical method is that you need this chloride mediums, lithium chloride and potassium chloride mixture, molten phase, which is available only at greater than 700 degrees Celsius. Now, can you really have a melt at room temperature? Yes, it is possible if you take the room temperature ionic liquid. So for that, what you do is, this electro refining is done in this case, as it is done. You take the metal and is a room temperature ionic liquid and then carry out the processing by applying the voltage, and you can get actually the metal ions from this room temperature ionic liquid. Yeah, just a few. Now, what is how to go about this? So we can do the selective leaching. So we have carried out inter-room separation also. And here uranium peroxide we have taken and dissolved in the room temperature ionic liquid, taking this solvent, this is a DEPA. And this has shown that very nice prospect it has shown. For this we have carried out the separation using other metal ion also. And finally, just madam, last one. This is the very challenging problem which is the Indian rare earth has been facing. It's the neodymium separation from the praseodymium, which are the adjacent rare earth molecules, elements. And the problem is that if you do carry out the hydrometallurgy steps, which actually is done in the Indian rare earth, the problem is the separation factors are only 2, because you need hundreds of cycles actually to carry out so that you get a better separation. So what we did is we have used the room temperature ionic liquid and we exploited the lattice energy difference in this neodymium oxide and praseodymium oxide. And see the huge difference in the lattice energy, and it suggested that neodymium you can easily leach out from this oxide compared to praseodymium.
So electrohydrodynamics basically has several applications in the field of microfluidics. So where we can see the water in oil emulsion, they can feed in one side and we apply the electric field. It starts flowing and then we can separate the two phases. Then the other application we can see the droplets are basically breaking up under the electric field. So we have plate electrode two sides and they are elongating along the electric field and they start dripping. Stream dripping, and we can get a very equal size micro droplets. Then we have a major application in the area of coalescence. So here we can see the two droplets are basically under the electric field and they make a dipole and they are approaching to each other. They will make a contact at a certain point and they will coalesce. The other major application of this electrodesalting in petroleum refinery, where we have water in oil emulsion systems, it has to be separated before sending to the downstream process of the refineries. And then again, electroemulsification has application and electrospray. So I'm going to discuss mostly about the electrodesalting process and their applications. So we know the crude oil basically we are receiving from wells or offshores. It goes for the settling time where the major amount of salt, sludge and all is removed. But still the water that is present in oil, they are basically in salt water and they have very high salinity. It cannot go to the downstream process for the before doing the electrodesalting process or electro operations. So we do this and the main motivation is this: we have to treat this crude oil, otherwise the corrosion cost is again going to be 50 to 60% higher than the for the maintenance and all. The second, we know we are already running out with the good quality of crude oil. So it seems that India is also looking for the more and more drilling, and we are going to drill for the opportunity crude oil. Opportunity crude oil is basically where the crude oil not in good grade, but it has waxy and other high sparkling concentration. So in this, we have to develop our own electrodesalter systems. So if I come to the operation, so this is, let us say, cross-sectional value or image of a desalter. It has basically very big, 2 meter in diameter and 10 to 15 meter in length. It has consecutive electrodes, so we can have crude oil, we mix with the desalter and fresh water and we put the emulsion here. And we have series of electrodes connected alternatively, positive electrode and negative electrode. And under the electric field, the droplets starts going and they settle at the bottom, and then clean oil can be go to the downstream process for the refining. Here the water is less than 0.05%. Okay, so very high to understand what is happening onto the internal like in this big basin, we have choose, let us say, 2 droplets under the electric field. We put these 2 droplets under the electric field and make the very high electric field. It can control with by the function generator and all, and we find out when the droplets make a contact, it forms a cone angle, and half of the angle we call as, let us say, cone angle, and that is, we found that experimentally this is going to be derived, my droplets are going for the coalescence or not. So let us say this is the coalescence phenomena we have seen. And this is certainly we call non-coalescence phenomena, which is we don't require particularly for the separation operation. Okay. So what is happening from this to this? This is not only the electric field, so it has various parameters. So it's, let us say, if you are assuming we are going to increase the electric field, the rate of separation is going to be very fast. No. So it has a negative impact. It will show non-coalescence event, and then there are other parameters also dependent. So we have done very systematic studies with respect to different electric field we applied for the two droplet system, and we try to match the Pohn-Engel criteria. But we found that at certain electric field, both coalescence and non-coalescence regimes come. So to identify this, we know the dependence on other parameters. To convert this information, we choose a non-dimensional number. We choose electrocapillary number that has a electric field, interface density, and size of the droplets. And then we transform these results, and we found that at certain Pohn-Engel, beyond that, it is always going to show a non-coalescence phenomena. So we have to keep our electric field or other parameter in such a way so that this critical capillary number has to be low side. And again, we found this is a dependence on the conductivity of the droplets, which is basically decreasing as we increasing the conductivity. And so this is we first time reported this low non-coalescence angle. Initially it was reported at 45 degrees. I skipped that introduction slide, and we published this. Then after that, this is a very clean system where we have just took two clean droplets. Whereas when we took original droplets that is coming from the crude oil, it has, because all the water flooding, core flooding, and polymer flooding happens. So it's either droplets can have polymer based or surfactant or combined of this, and this has a very greatly dependence on the electric field or electrocapillary numbers. This is basically decreasing with respect to the concentration of surfactant and polymer we are going to increase.
Conclude now.
Yeah. So skip this. Okay. So then further we have done the experiment with respect to the water droplet interface, and first time we also tried to get the information in terms of what is happening during the bridge formation. So here we can say this is going to make a bridge, and then it appears as light droplets. We scale it out, and this is the main region we are saying the electric field is basically pulling upward, and the gravitational force is downward, and that can be scaled as like the inverse to the electrocapillary number. And then we also find out how the transition from partial coalescence to non-coalescence is happening. So I will skip this. I will come to the electro. So generally we, let us say we want to increase the rate of separation, so we try to increase the electric field. So let us say in coming practice we are using this mode of frequency. So we proposed modulated electric field. So we propose some time period the electric field will be very high, and some time period the electric field will be low. So what will happen when we have droplets very far, they will approach to us very near to each other, and then when the electric field comes into the low electric field, they will coalesce. So the non-coalescence criteria will be reduced. So if we see the like immersion level, so these are the, let's say, water immersion system. When we apply the high electric field, they will make chain, and when this low electric field region comes, they start coalescing. And then we can repeat this phenomena, and then we can have very fast separation of droplets. And this can, and then after that, doing this fundamental study, we have studied this all setup at different scale from the 50 m to 1 liter to 500 liters.
Please conclude.
Yeah, and so this is the 1 liter setups, and I will just I take 1 minute. So apart from this, we have also developed a mobile oil treater where the crude oil well's capacity is very small, so that transportation of the crude is very high. So in that case, this kind of tailored mounted desalters can be deployed on the sites, and they can be treated the crude, and then treated crude only can be sent to the site for the further operations. And we got this all the design internals, and we got a grant also, a patent. And recently we are in contact with a few manufacturers, so they are interested to scale it up. So I can summarize here. Thank you. So we first time we reported low contact angle fluorescence, and that we have also scaled the partial fluorescence to non-fluorescent transition like capillary number to the Reynolds number 0.5, which is showing capillary number has higher impact as compared to Reynolds number. And that's okay. And the modulated electric field we have found out is basically mitigate the chain formation while applying the very high electric fields. So thank you.
Thank you.
So I come from CSIR. CSIR has a network of 39 labs across the country. I am from CECRI, which especially works on in the field of energy, where it comes. So if you see here, so we are located in south part of the country. Our headquarters is in Karaikudi, and we have a facility in Chennai, where the most of the work happens in the field of fuel cells and the lithium-ion batteries. So this is the outline of the work. So directly going to the motivation. So we already know what is the issues which we are facing with the CO2 and what is our net zero target by 2050 and 2070. And today in all this, the one of the new fuel which is coming up now is the hydrogen, which plays a very critical role. How we want to generate the hydrogen and then how we want to use the hydrogen. So today I'm going to talk about how we are going to use that hydrogen in terms of fuel cells. And if we see the market of that fuel cell, it is pretty good within in India. So this is one of the technology which is the proton exchange membrane fuel cells, and the market size within India is pretty much is pretty good, and it is going to go up by with a percentage of close to 20% CAGR. So just to give you a brief, what is the fuel cells technology? So the fuel cell
You can skip this, most of this audience.
Okay, sure.
You
So-
go ahead to what please? Your
Fine, fine. So just to give you an idea, so why we have to make a fuel cells, because the operating voltage of a fuel cell is 0.6 volts. So we have to stack multiple cells into series to make a fuel cell stack. So again, these are the various components of the fuel cells, and this is I'm only talking about the fuel cell stack. Again, when you have to make an engine, there are several BOP components which also takes part into it. And the one of the major component, which is the MEA, membrane electrode assembly, which is the heart of a fuel cell, and how we define the performance, which is this from the curve, which is the VI curve, where you want to shift this curve, which is in blue, in the direction of upwards, so that you can get the maximum power output with the maximum efficiency as well. So the problem statement, so if we see there are total 25 parameters or so, which kind of governs the fuel cell's performance, and the electrical power output is the function of all these 25 parameters. And the challenge is how can we achieve the targets which is already set by the DOE, and so that when we achieve those targets, the cost of the systems can also come down. So what we have done, we have taken from the lab scale. So the one of the major components is the MEA, which I said that which is close to 14 parameters. So we have gone from the catalyst powder, which we use which we make in the lab, from making that powder in a small batches to a large batch production. Then going from powder to the catalyst ink, from ink to make the catalyst coated systems, and then how we can optimize all these parameters in a way that you can get the maximum performance from the system. So it becomes very tedious job if you want to do the number of experiments by varying one parameter at a time. So we have gone through with using the design of experiments, where we have fixed few of the parameters. And so some parameters was fixed, some parameters was varied, and then keeping the operating parameters also constant, we came up with close to 19 to 20 experiments. We performed those experiments, and then with the help of the software, we finally and all the experimental data which was generated in the lab, we came to a final optimization ratios of all the solvents, the ionomers, the membranes, which is the good for us. And then parallelly, since we were working with the companies, along with this, so the whatever process which we use, we want to scale up that process as well. So earlier when we want to make an ink, we were making an ink using a perovskite method, where you cannot go more than 10 ml at a time. So we shifted from perovskite to ball mill method, where now we can make an ink of 200 ml or 500 ml in a single go in a less amount of time. Similarly, when you want to make the electrodes, so we were earlier using the blade coating, doctor blade coating. Again, the output from this is, you can make maximum 20 electrodes in a day. Now we shifted to the method where you kind of do a fine spray directly on the membrane, and with this we are able to make 500 plus kind of CCMs in a day. And the one of the other which is really help us here, so when you do a Dr. blade coating, you do a coating on a Teflon sheet substrate, then you transfer that onto the membrane. In a spray coating, you can directly coat on the membrane. And the one of the issue which we face, when we do a hot pressing, you put a mechanical force on the electrode. So the pore size which is there in the electrode, that got lost. And the one of the issues in the fuel cell is the diffusion of the oxygen. So you want higher pores in your electrodes, which we were able to get it when we use the method directly coating on the membrane. Similarly, from the area perspective, in the lab, we always do a testing at a 5 square centimeter, 25 square centimeter. When you want to do a technology, you have to go to a higher areas so that the number of cells can come down. So we have increased the area from 25 to 200 square centimeter. We have used the I would say method for that. One is one tool which we have used the Thomson multiphysics, where we have optimized all the flow geometries, and along with that we have also used the CFDs, so that we know that the flow across the active area is uniform. So with this, we could able to increase the performance by 100% from 1 amp per square centimeter to 2 amps per square centimeter, and the total volumetric power density, so that the size of the stack can be brought down. You could get for a 3 kilowatt stack from 0.7 kilowatt per liter, we could increase that density to 2.5 kilowatt per liter. And with this, since we have used the lower number of MEA, so the total cost also came down by close to 30% per kilowatt. And by doing all this work, we could able to do a technology transfer. So we have using the very first technology which is made in India, we have demonstrated this car, which is a part of a CSI and MITRI program. The work jointly done by SICRI and NCL at that time. And this is a 10 kilowatt stack tested in the lab. Then the same stack was retrofitted in the car. We have done this demonstration, did a technology transfer to KPIT. Later, the whatever SOPs which we have made using the same SOPs, same technologies, KPIT has now made the technology at a higher scale. They have gone to TRL9, where they have shown now first bus powered by the indigenous fuel cell system, and now the first small ship, a passenger vehicle, which is now being commissioned also just last week in Varanasi Ghat. So the upcoming work, now we are also scaling up internally in the lab. We are now focusing on the engine development. Now we have new targets for 2027, 2028. We are working with 4 different partners with us, and we are going to demonstrate the fuel cells powered submarine, 3-wheelers, drones, and tractor applications. So we are also going to expand our expertise in the lab. So thank you so much.
First of all, I'm overwhelmed by this honor, and when I was asked to make this presentation, I was thinking how to plan it, and I decided that I will just give a very superficial brief overview of my research activities after coming to IIT Delhi. And of course I have 2 of the seniors sitting in the audience. Professor Murthy was there when I joined, and Professor Bhimsingh was my head at that time, not at the time of my joining, but later on. So yeah, I feel nervous presenting in front of them.
Honored.
Thank you.
We have come here to give you the support.
Thank you. So I stand on the shoulders of my PhD students. So these are, I just thought I would just first start with the talking about the work, because the work that for which I have been recognized is the work that was done by these boys and girls. And about 19 PhDs have graduated under my supervision across the last 18 years. 19 and 18 years, yeah. And many of them are now in different IITs, or they are in the industry in India as well as abroad. I am currently the Power Grid Chair Professor at E Department, and I also am looking after the Renewable Power Center of Excellence on Energy and Environment at IIT Delhi, which is a multidisciplinary Center of Excellence, brings together researchers from all departments within the institute who are working in the area of energy and environment. So my PhD was in the area of power system stability and dynamics, and after coming to IIT Delhi, I was exposed to a large variety of people working in the area of control, in the area of power electronics, mathematics, signal processing, sensors. And so I diversified into wide area measurement systems. I diversified into renewable energy technologies, specifically wind turbines and solar photovoltaic arrays. And lately, two of my students have started, well, three are working in the area. One of them has already graduated in the area of data-driven analysis and data science, but all in the general flavor of power system dynamics. So I'm supported by a lot of people here. These are just some people I was trying to come up with who have supported me, and this is something that, so I just thought I'll give you a brief overview of the recent work that has happened in the last about 6-7 years. This was a white paper that I and my colleague worked upon in IIT Delhi, Renew Power Center of Excellence, which looked at the flexibilization of the Indian grid. And subsequently, this white paper came out in 2022. We talked to a lot of industries as a result of, as part of the process of coming up with this white paper. And so it was a very learning experience, and subsequently all my research has been focused on flexibilization of the Indian grid. So I start with that. Flavor that whether the Indian grid is flexible enough. And these are some of the contexts. These are taken from the white paper actually. It's there online if you wish to see. These are some of the contexts that is there in the Indian grid, because we have a lot of renewables coming in. And the distinguished speaker was Panda, who just spoke about converters. I look at the system perspective. What he's talking in the device level, I'm trying to look at the same device but from a systems perspective. And I'm looking at whether these converters, which are very essential to integrate the renewables and meet our carbon footprint goals, whether these have an impact on the system stability, system dynamics, because eventually the electric grid, if the grid is not working, however nice devices and controllers you build, you will not be able to reach the power to the final utilization. So the electric grid is the vehicle of renewable energy integration in the country. So some of the very interesting facts as a result of high penetration of grid. By the way, Indian grid is one of the largest grids in the world, and we are in a relatively better position in terms of flexibility because we have a lot of coal, and also we are very big. We are very big, so if we fall, we will fall very hard. But most of the grid operators to whom I talk to, they are quite confident that we will not fall. Some of the key issues that need resolution, which we at IIT Delhi are working, I and my colleagues are working, are specifically the impact of high renewable energy penetration. So for instance, if you look at monsoon season in July, when the wind and the loads are high, that's when the load, all India load hits maximum. So you have maximum peak to off-peak demand variation, and at sunrise, when the solar ramps up, the renewables have, the thermal generators have to be ramped down, and at sunset, when the load goes up and the solar goes down, then the thermal generators have to be ramped up. So you have evening ramp up rate and sunrise ramp down rate. These are some numbers which are very difficult to achieve in India as of now. So these solutions that I'm talking about, except the first one, which is a mechanical engineering problem, the remaining three are something that I and my PhD students have actively contributed to. The first one is, of course, the fact that thermal generators, because of the boiler constraints, cannot operate below 40% of the load. So there is a minimum technical limit. So you need to operate below that in order to keep connected. But the others are all electrical engineering problems, which are that the fact that you must have converters which can mimic the action of synchronous generators by maintaining voltage and frequency. You need to have a grid which is very big. It does not move very easily. The frequency is very steady and the voltage is also very steady. it has very high fault current levels, and of course the uncertainty that is there because of the renewable energy, it needs to be managed. So the next, I have about 7-8 slides, so I will finish on time, please don't worry. And I'm going to very quickly give you a flavor of all these. And whatever I'm presenting has not been done by me, but my PhD students again. So this is some typical power system frequency that has been captured in India, all across all India grid. So this is a typical dip in the frequency from 50 to 49.7 because of a loss of a large thermal power station. And there are associated oscillations. These oscillations are typically the generator rotors which are rotating at 50 Hertz. That 50 Hertz is actually not 50 Hertz, but it's oscillating around 50 Hertz. And that is what this oscillation is talking about. So if you do a coordinate transform and you make everything that is at 50 Hertz, 0 Hertz, then you can actually project this on a much better visually it looks much better when you have simple sine waves that are damping out. These are actually damping out. So the fact that the frequency is dipping is a different problem, and the fact that the frequencies are oscillating while they are dipping is a different problem. So I address both those problems. And I have, we have seen that both the dip as well as the oscillation, how big the oscillations are and how quickly the oscillations die out, are affected when you have a lot of renewable energy penetration. So, for example, in this kind of a graph, so this was some PhD, this was in the PhD thesis of a student who graduated in 2019, just before lockdown. And he showed that when you have different penetration levels, for the same load change, you can have a deeper frequency dip because the system inertia is lower when you have more renewables integrated. Similarly, it is not just the change in the load, but also the change in the wind, which now starts creating problems in the frequency. So, typical change in the wind is something like this. If this is a output of a wind turbine, it varies because the wind is varying, and so this will result in this kind of oscillation in the frequency. Another PhD student who graduated about 2.5 years ago, just after lockdown, he was working with what is known as converters, grid following converters, grid forming converters. These are converters what Professor Panna talked about, but I look at it from a systems perspective. So you have a grid following converter or inverter, and you have a grid forming converter. So following means it follows the frequency and the voltage of the grid to which it is connected and just injects active and reactive currents to maintain certain power output. And the grid forming is something that maintains the voltage and frequency, so it can actually operate in isolation. It does not need to have a synchronous generator. So it's a current source and it's a voltage source. And so the dynamics are completely different. And in India, we don't have grid forming technology, grid forming converters deployed yet. Right, sir? I don't think we have.
Very much less. Only you have a, if it is a magnetic grid, then only, very rare.
Yeah, so, but outside India, people have already started deploying grid forming technology because it is something that is the future way forward. Grid following is, of course, widely available in India. So the dynamics are all, of course, the way I look at it, the dynamics are second order dynamics, and there is like very established, nice mathematical analysis of the impact of these technologies on the grid frequency and the grid voltage. This is one girl, she is now just submitting her thesis, and she's worked on this uncertainty that is coming from the renewables, the fact that you have a dynamic system which is being subjected to stochastic disturbances. So how to analyze such a scenario, how does the system modulate those stochastic disturbances such that the measurements that you obtain from that such a system, those measurements themselves become stochastic. And is it possible to recover the nature, the statistical nature of the inputs from the statistical nature of the output? So if I am observing the voltage and the frequency, I find that they follow a certain statistical distribution, the stochastic characterization. That statistical characterization would probably match the character of the inputs. So this is something that we are exploring, we have explored, and one very nice observation is the fact that there is something called ergodicity. So power systems are ergodic in nature, but only for certain time windows. And identifying those time windows is very important. Ergodic means that so if you have uncertainty, then you may have multiple realizations of the same dynamic system at any point of time, and the mean of those realizations is equal to the mean of the time series within that window. So that is one way of looking at ergodicity. So there are other, of course, much better definitions of ergodicity. So the power system is ergodic, but only within a time window. And one of our research outputs has been to identify, is to come up with a methodology to identify within what time window the power system is ergodic. Once you have ergodicity proved, then there are certain statistical theorems that you can apply. My final thing, this girl, she's now almost at the end of her PhD, so hopefully she will submit by summer. She just got married, so I don't know, that will change things a little bit. But so this is parameter sensitivity. So this is something that goes back, very established theory on how small signal behavior of a system is impacted by the change in the parameter. So if you look at any standard book in linear control theory, then you see that the eigenvalues are perturbed, and the perturbation in the eigenvalue can be measured very easily by this kind of a very simple sensitivity index. And so there are limitations to the sensitivity index in the context of power systems particularly, where we say that the change in the parameter not just directly modifies the eigenvalue, but it also changes the operating condition, which in turn has an impact on the change in the eigenvalue. So there are two ways in which the change in the parameter can affect the eigenvalue. Now somehow we find in the literature that this path is neglected. As a result, the sensitivity that you calculate using this formula for a certain class of parameters can come out to be very erroneous. So we have come up with a different way, like modification in this formula, and that seems to work quite well. I don't know what we will use it. We will probably use it in future if she comes back after marriage. We will probably use it for some things like controller tuning.
I'd like to thank INE, my nominator, and review committees for seeking or considering my work worthy for this fellowship. So thanks. I also thank my parents, my family, wife, children who have sacrificed and inculcated the energy and passion in me. All my teachers, professors, students, because I was also in academia, students as well as my colleagues across my academic life as well as my industrial R&D career. Without whose support, this would
one
not
small
have
suggestion, Dr. Barbie.
Yeah.
We don't write F-I-N-A-E, we write F-N-A-E.
been. Okay.
I know. So we have to do it.
Okay.
I know.
So with this, I would like to thank. I will correct it in the subsequent readings. Now, so as we know, the energy transition is mainly happening because of lot of renewable penetration to the grid, and compared to traditional grid, the grid scenario is completely different now, and that calls for certain aspects to be covered, and that's what I will be. Couple of cases I will be talking about. Before that, I would just like to give a quick overview of my journey. So, I've been PhD MTech on Systems Control Engineering, IIT Bombay, BTech Instrumentation Control Engineering. I've been more in systems control and optimization is my area of work across, including interdisciplinary systems. So throughout career, I have worked across chemical process control. I worked in robotics automation, manufacturing automation. I worked also in the certain systems and control board design problems in very distributed technology, exploring that, building prototypes, giving proof of concept in magnetocaloric refrigeration, which was one of the very satisfying work, very low TRL work, transition to business so on, later on, and so on. Across this career, I have almost more than 21 patents and 50 plus international journal conference publications, more than 15 actual real products where I have a contribution. Of course, it's not individual contribution. Many of these programs I contributed, many I have led myself along with the team and basically conceptualized and took it down to the product. Because in G research, what we work on today actually goes into product some few years later. So it's a this research center basically fills a gap between academia and real products. Right? So product engineering teams, technology teams, which are lying in the business. And as a G research, I was a part of the corporate research. So we worked across different businesses: power, energy, healthcare, oil and gas, locomotives, transportation business, and so on. Last 2 years back, there was a split in GE, as many of you would be aware. So I'm part of now GE Vernova because majority of my work has been focused around the power and energy. So I prefer to be as a part of Advanced Research Center in power area, which is GE Vernova. Aerospace got split separate and healthcare got separated. Of course, but I worked across all these businesses. And GE Vernova is again, for information, it's again like a mini GE. So it caters to all the different areas. So right from coal plow, it has its products. It's OEM, right? With high technology products in coal, gas power sector, nuclear, hydro, grid, solar and battery, and wind turbines. GE has one of the leading producer of wind turbines, and grid solutions and grid automation areas. So I work across multiple, most of these businesses except nuclear, hydro, and so on. In academia, I have of course guided a few PhD scholars and of course MTech students and so on. So across technical domains, I work mainly across advanced process control, model predictive controls for the process controls, model-based controls, optimization, instrumentation, IIoT systems, microgrid, analytics, industrial automation, and robotics in the manufacturing sector. Application domains has been, as I already mentioned, fossil and renewable power generation across coal, gas, biomass. Explored a few years in biomass. Gasification with IC engine, gas engine integration. Solar PV being basically distributed hybrid distributed power generation system, which I will be talking about here. One of the example. Worked in the area of UAVs, cement plant. When I was earlier career, I was at TCS. Also worked in cement plant optimization. It's again catering to sustainable energy, right? So where you want to minimize the energy consumption by the loads, so industrial loads. So cement ball mill, cement kiln, optimization of those. So you can save, and we could demonstrate in the real cement plants up to say 10% of energy consumption. Specific power consumption by cement ball mill, cement kiln 1.2%. 1 to 2% of specific fuel consumption we reduced based on the water predictive control solution at supervisory level, doing the controls and optimization of the cement plant equipments. I have been an IIT fellow. I also received ISA fellow, International Society of Automation. I have been part of that, which is again global organization similar to IEEE and IFAC. I have been associated with all the professional organizations. Within GE also I got several awards. And yeah, so this is all in brief about me. Now, so this couple of early slides, many of you would be already aware. I don't want to go into details of each of the slides. It's just collection of some information. So, if you see, the electricity is a measure of any growth of any country, any society, and so on. So, how much is the electricity consumption? That is an indicator for any country's growth, or any geography's growth, or any society's growth. So that the first chart shows that. So if you see the countries which are having a social progress index which is low, they are having their energy consumption or energy demand is also low. And countries who are considered more developed, their energy demand or energy consumption is more. So electrical energy or electricity is considered as a measure of country's growth, geography's growth or society's growth. And all the countries have to grow. So as countries start growing or they want to develop their communities, of course the electricity consumption will increase and demand will increase, right? But if you see, this number may be a little old, maybe around 2015-16, 2 billion people in the world. Many of you, we might not be aware, because in India we have good electricity availability now. Of course, 10 years back I have personally witnessed villages where there was no electricity. Some of those we contributed to rural electrification program, which I will talk about. But world over 2 billion people are still not having access to electricity, or they have a very poor access to electricity. By poor access, what I mean is they may have maybe 4 to 8 hours of electricity in a day, and most of the other time they may not have electricity. Now 2 billion people, if you see, world population then was around 8 billion. If you consider it's a 25% of world population who doesn't have electricity access, which is very surprising to know, or very painful also to know. And majority of those are in global south countries as well as some developing countries and so on. Now, so that is one information. Second is, if you see electricity use, household electricity use, again developed countries versus developing countries, and those unaddressed countries, that pattern is visible. Growth of electricity demand across industrial, residential requirements and so on, their countries is growing, right? There's a third chart is what is showing that globally. Whether it's a developing country or developed countries, there also demand is growing. Developing countries, the demand growth may be more faster compared to the developed countries. Continuous rise in emission has been happening. If you consider the traditional production of generation of electricity, which was there maybe 3 decades back, right? 3-4 decades back, most of the generation was traditional with fossil resources, very little non-fossil resources in the generation. If you consider the solar, wind, and biomass and so on, they are not emitting while producing the power, whereas fossil are producing power. So they are culprit. So fossil power generation is a culprit to do the global warming. Right? And slowly learning this over last 2-3 decades, countries have started diverting. So instead of fossil power, generation has started moving towards the renewable powers. Solar particularly, little bit hydro, very small nuclear, and wind. So solar and wind will be the major components of the mix. This again chart shows the same in terms of demands. Which is residential, commercial, transportation, industrial. The demand is growing in developing countries, which is the non-OECD countries. Demand is growing faster in all these segments. These are the different industry energy users, right, or electricity users. And demand growth is there, but it's slightly slower in the developed countries. Now, this again gives a number about the power per capita primary energy consumption. Again, there you see the developing countries or non-OECD countries, that numbers are low, and those numbers have to finally actually grow as time goes by. So, particularly what I want to convey is, though we know the electricity is a measure of growth indicator. Growth of across the world is going to grow. We know traditional power generation has been fossil, and in the mix of overall power generation, that is still high. So, as the world over demand is growing, you need to add more and more power generation. Part of that or majority of that still might be fossil based, and your emission is going to grow, global warming is going to grow, and so on. So those problems had to be addressed. And last decade or more, world over have started seeing climate changes. Right, we are feeling that there's been impact of global warming. Maybe 2 decades back versus now, it's very significant and visible. So countries across globally have started thinking about it, and they are more and more serious now. And this is, I won't go into, sorry about the chart, but I don't want to go through details, but what I want to convey here is a net zero pledge as started. So all countries earlier, they were talking about we will reduce our carbon emission, global warming, we have to reduce. Spuriously some experiments or some measures were taken, but now countries have come together and across the countries as well as across even organizations like major industries and companies, different organizations, they also started pledging by 2030 we will reduce our, we'll become net zero. By 2040 we will become net zero, like that. And India is also one of them across all the countries. We initially pledged 2050, but then later on we changed the dial and we said by 2070 we will be net zero. And these are the proper commitment, right? It's not only we'll do some measures and all. So every country has started committing. Now, so that means the countries have to take actions. Now, what are the actions which has to happen? So, as I mentioned, all of us know solar, wind, that's the major component which will come into the grid now, right? Now, if you see fossil power, they are controllable. And solar, wind, they are nature-based resources, though they are renewable, they are great for the emission point of view, for the global warming point of view. But this energy resource, this resource is variable. It's distributed, it's not lumped, right? So if you compare the coal or oil, it's a lump. If you see the power density is very high. So within the size of power plants, a coal power plant or gas-based power plant, amount of electricity which you can generate, it's 500, 600 megawatt in a small gas turbine, right? Couple of gas turbine. You can generate of that level. And for the same level of electricity generation, the solar farm, it will be spread across kilometers. Wind farm will be spread across kilometers. Again, your source is not controllable. In case of coal or fossil, source is controllable, right? You can control how much fuel you want, how much you want to generate. You will add the fuel or reduce the fuel. It's controllable in your along with you. So if you see the scenario, so how the energy scenario is changing. So if you see the left side, hybrid power generation in transmission grid. So this is a traditional grid, which is having a centralized fossil, coal and gas-based power plants. Large central solar grids are happening now, adding up now. Hydro nuclear are very small components. If you see the scenario which is changing, because solar and wind are growing and they are distributed, it makes sense to have this generation near the load centers. Right? So earlier, if you see the grid scenario, power generators were at one side and electricity is distributed, transmitted and distributed. Distribution side, you don't see much of the load generations. But now, because these are inherently distributed in nature, solar and wind have started coming into the home, right? Your rooftops and so on. So distribution side also your generation coming up. So grid is becoming more heterogeneous, right? So originally your homogeneous grid, transmission, generation at one side, transmission and distribution, and then you only load on the other side. But now grid behavior or grid patterns, operations patterns are changing, and so distributed generation is rising, and that is creating problem in terms of grid stability, resilience. Grid inertia is changing because you have more and more. So earlier, maybe 20 years back, in the mix, fossil was hardly, fossil was around 90%, 10% was other sources of energy or generation. Now it's growing to, mix has been becoming towards 50-50, right, or 60-40 and so on. So grid is becoming weaker because this solar and wind are actually inverter driven, right, converter driven, which does not have inertia. Whereas fossil are all based on synchronous generators. So you have a large inertia which is running, and that's causing grid becoming weak because of this. Similarly, so that has to be addressed. So that scenario has to change. And second one is your power usage side. You have to make loads which are more and more efficient, right? So you have to take measures in this direction. Out of this, so now coming to two accomplishments which I wanted to talk about. I'll take few minutes.
Not more than 2 minutes.
Okay.
We are
Okay,
already
yeah.
running.
Fine. So two contributions which I projected out of my multiple work is, one is on the left side, which is we developed, this was work done in academia through my PhD scholar. I was a co-guide with the guide in IIT Bombay, and we developed a boiler, lab scale boiler prototype, which is not using the fossil fuel, but because we wanted to have a more controllable. So it's an electrical boiler which we developed, and this boiler could, so if you see the boiler operations, boiler drum which is having a water and steam combination, you see inverse response phenomena, right? Swell and shrink phenomena. which is not easy to build or develop or showcase or design into small size boiler. Fortunately, we could come up with a design wherein we could create that scenario, and that created a very good lab setup on which PhD students could work on. And we actually were looking into, the work was focused just to meet this energy transition requirement. That's how to make fossil plants more agile, because now more and more renewable are coming. Fossil plants also have to change their behavior, because whenever needed they have to come up, whenever not needed they have to come down, because then rest of the whenever power is available on solar and wind, my fossil fuel should generate less, and so on. So that agility and flexibility has to be brought in, which was not the case in the original traditional grid operations and traditional power plant operations. So to do research towards that, how to make my fossil plants more agile, how my boilers can act fast and flexibly, that is one area. Second one was, we came up with for areas which does not have grid, access is not there. In those areas, how to provide the grid? Can we skip the grid and come up with a solution which is solar, battery and diesel genset based solution, which can locally generate, islanded mode, it will generate and distribute the power locally. So that was the rural electrification product which we developed. And good part was this, we started from research, lab development, lab testing, we take it to pilots and finally take it to product. And as a research team, I was leading that whole systems and digital part of platform of that. I could got an opportunity to work across all, not only to work and deliver it, but also went to the sites, rural areas, and did installations and tuning of the operations. So this is the other work which was the contribution. Yes, I just play this and one more. This will showcase. It's an African village where we installed this solution, and you can see the instantaneous, spontaneous reaction of the people who did not have electricity once we put up this. And these are small 15 kilowatt, 30 kilowatt solution. They are parallelable. I can generate up to 150 kilowatt. As my village requirement keeps on increasing, I can keep more and more these blocks in parallel. And fortunately, I could personally witness this when we installed. Actually, we were testing our system when we installed. And suddenly the villagers, they came on when they saw the light, and they started dancing around. This was very pleasant or happy feeling that how science and technology can contribute to and change the people's life. I could witness this person. Now you might say, just one more slide. You might say, okay, this is very simple. What is the differentiation there, right? Because I can have diesel genset, I can have solar inverter system. They are available. I can just connect them and connect it to island. I can do it. I can connect it and get the power. The differentiation which we brought in this, because inherently we wanted to have it islanded, and if you see islanded, that means my load has to match my generation has to match the load. And in village areas or even otherwise, your loads are very low in the night, right? In the later evening and night, and that's when my load requirement was coming all the way up to 10%. And if you see the standard fixed speed genset, you cannot operate them below 30% load. So that is where we brought some differentiation, and instead of synchronous generator based fixed speed DG set, we actually put down the variable speed genset. We converted them into variable speed, but then my frequency will vary, right? Because instead of I am using still a synchronous generator. So change the synchronous generator, borrowing the concept from wind turbines, we use the W-fed induction generator, and that allows us the flexibility and controllability. So we could still maintain the frequency 50 Hz or 60 Hz when it's required, but I can still load down my genset up to 5 or 10%. It gives me 10% more overall system efficiency, power generation efficiency, which was usable, which was very right for the technology. So that's not what we say. You understand the problem, you find the need, and then try a solution which will match that rather than using the basic concept. This is where we brought the innovation. Second thing is, it was inherently targeted toward the rural areas. So we integrated right from the design stage itself, we integrated the digital platform. So over cellular network, we can monitor this turbine, our hybrid distributed power generation system, because you cannot have engineers in power plants, fossil power plant. You can have qualified engineers who might be operating those plants and doing maintenance and repair. But in rural areas, you cannot have qualified people available. So just ITI person or technician, diploma technician can operate this plant, maintain that plant, but then you need those plants to be tuned and subsequently also monitored. So we developed the digital platform. Over a cellular network, we could minute to minute, we can receive the data, and we had a complete dashboard. And we added some of the supervisory control solution using mixed integer linear programming to do energy management. Looking at 24-hour ahead forecast, and then you can basically dispatch plant preparation and so on. So that's the overall solution which we're building. Because of less time, I cannot go into more details, but at some other point, whenever we get a chance, we can cover this. With this, I'd like to just.
So basically, our research group worked in a few areas. The one is the hydrogen energy storage and purification combustion. Another is the porous radiant burner, which can be used for both cooking and as well as industrial application. And we also work on the soft heating and cooling system, which includes the AC and cooling system. Then we also work on the solar drying related areas. Okay, so coming to this in this present one, and I will talk about the design and development of porous radiant burner, what we have done at of course this work started at IIT Guwahati, and then of course we have done it from IIT Tirupati. So the India is the second largest consumer of LPG, and our consumption is roughly about 33 to 34 million metric tons of LPG per year. And more than 50% of LPG we import from other countries. This is a huge financial burden for the government of India. So we wanted to cut down the rate by 2030. Our government is planning to cut down the LPG import by about 15 to 20%. And at the same time, we need to also provide 100% clean cooking fuel. I mean the clean cooking fuel to 100% of population by 2030. So if you see the scenario. The thermal efficiency of the stove what we have in the market is relatively very low, which is about 60 to 63%. This is for the domestic. If you go for the commercial, high capacity burner, for example, which is used in the college, the education institutions or the hostels and the restaurants, their efficiency in fact it's lower than 20%. And besides having low thermal efficiency, if you see the emissions which are much higher than the standard prescribed by the World Health Organization. You know most of you are aware of the operating principle of the cook stove. So when the LPG is injected through the nozzle and because of the high pressure, and then you have the at the nozzle, then you have because of the high velocity the vacuum is created, then you have the natural air environment. When the air fuel mixture comes at the top of the burner, then you can have the combustion. This is the pre-flame combustion, and there is a standard for the measuring the thermal efficiency of the burner. For in case of the domestic, we have 4 to 4.6. Then for the commercial and biogas, we have the separate standard. So basically, the efficiency need to be tested by conducting the standard water boiling test. Like you take the predetermined amount of water in a particular size of aluminum vessel and heat the water from ambient temperature, say about 30 to 90 degrees Celsius. During this process, the energy consumed, the LPG consumed multiplied by the actual calorific value gives the input. And output is the enthalpy gain of the water along with the vessel. So the output by input gives the thermal efficiency. If you see the conventional burner has the thermal efficiency which is used in the domestic application has the thermal efficiency in the range of 60%. But if you move to the higher capacity application, even the thermal efficiency can be around 20%. And besides that, the NOx is too high, and in fact the CO also too high. So then what we have done, so we have in fact in the conventional burner, the mode of heat transfer from the flame to the vessel is conduction. Since gases are having low thermal conductivity and low emissivity, the heat transfer rate is very poor. Okay. So then what we have done, we transformed the mode of heat transfer into the radiation. The radiation travels at a speed of light. When you transform the mode of heat transfer into radiation, then your heat transfer will be more effective so that you can minimize the heat loss. So with that concept, we have developed the so-called two-layer porous radiant burner. You can see here in the right side, the brownish color, that is the combustion zone, which is made up of high thermal conductivity, high emissivity ceramic material. This is again it's SiC, topped with some material, which has the emissivity in the range of about 0.9 to about 0.96, and below 1, that is where the line is, the white line is there, that is made up of low thermal conductivity, low porosity aluminum matrix. Basically, the down one is acting as a flame arrestor. So when you inject the LPG or any fuel through the nozzle, then when it travels through the mixing chamber, it gets mixed properly. When it reaches the combustion zone, where it gets combusted. Since the combustion is happening inside the highly conducting and radiating porous matrix, because of the volumetric radiative heat transfer, some part of the heat will be transferred back for preheating the incoming air mixture. So basically, this is based on the excess enthalpy combustion. Because of the preheating effect, so we could achieve almost 100% combustion efficiency. Since the mode of heat transfer is completely into the radiation, and then we could have the much better heat transfer with this preheating effect, and then the making the burner into the volumetric radiative mode, we could achieve the fuel saving up to about 60% in real time. Okay. So since the some part of the combustion heat point is transferred back for incoming air fuel mixture, we could stabilize the temperature around about 1000 degrees so that we can get rid of the thermal loss. So if you see in case of our burner, the temperature gradient across the burner is almost you can say negligible, within less than say 20 to 25 degrees Celsius. Whereas in case of the conventional burner, if you see this one, the maximum temperature will be attained at the center. If you go towards the periphery, you will have the temperature gradient more than 300 degrees Celsius. As a result, you have the formation of thermal loss. So we have developed the several, the capacity of the burner starting from the 5 to 8 kilowatts, and which give the savings about 40%. All the values are taken in the real-time cooking, not in the laboratory. Okay, we have installed nearly about 500 such burners in many IITs and many, the temples and the education institutes, and all these numbers are taken in real time. And then you can see that then we can also go for the clustering of 3 burner. We have done the clustering up to about 50 burner, where you can get the thermal output up to about 120 kilowatts. Where then we get for example, the commercial, the 7 burner, we got the efficient savings up to about 60%. And then we also extended the technology for many other fuel, like including biogas. Biogas, our burner works very beautifully because of the preheating effect. So usually the raw biogas, you will have the moisture content more than 7 to 8%, even 10% some cases, and CO2 also very high. Because of the presence of CO2 and the moisture content, the conventional burner will not work. You won't get the continuous flame. Whereas our burner basically it has the preheating effect. Even if you have the moisture content more than 7%, it will work. You can get the continuous combustion. So with the biogas also we have done it. And so this is for the domestic burner. Here we got the efficiency up to about 82%. Compared to the conventional burner, we got the savings up to about 35%. Now we are adopting the BA standard along with the LPG, the LERC, LPG gas recruitment research standard, which is in the final stage. Once the BA standard is published, and this will be also launched for the commercial application, for the commercial one. And so our burner not only provide savings up to about 60%, it can also save the cooking time to a larger extent. So we have done several such experiments, and you could see we can get the savings time anywhere between 20 to 25%. And then we have also done the detailed life cycle assessment. So the impact created by our burner on various the environmental mitigation categories, it's nearly about 6 to 10 times lower than the impact created by the conventional burner. So therefore, our burner is not only economically viable, but also it is environmentally safe. Then later we have extended this technology for the other liquid fuels such as the kerosene we have done, and methanol also we have done, and ethanol also we have done. And this is of course the support of the lithium. I am part of the lithium. And also we have also adopted the standard for methanol and ethanol, of course the cook stove also we have done. And then this is the summary of the things, and many already the porous stage burner operating with the LPG biogas, which is already commercialized. And now we are working on the DME, and we are working on the methanol and ethanol for the larger one, and also the other hydrogen based CNG also we are working, and we have done for the many commercial installation as well. And so just can I give you this so just for the video. So you can see here. So this takes about a few seconds to stabilize. Once it is stabilized, so you don't see the flame. It's a completely flameless. So during the operation, maybe someone can ask if any food particle fall on the burner, what will happen? So immediately nothing will happen. the burner will continuously operate. If any food particle fall on the burner, it will become ash. Okay. So nothing will happen. Whereas in case of the conventional burner, when you boil the milk spill over the burner immediately the flame will punch. So because of this reason only, most of the accidents happening in the domestic sector. And this is the burner which is installed in the temple. We have near Tirupati, we have a very famous temple called Agasti. Now the entire temple is equipped with our burner, and it's been in operation for more than 1.5 years, and they have given the annual fuel saving of about 40%, which is equivalent to about 65 lakhs. So this is the one. These are the larger installation, and this is IIT Madras. And recently we have, this is the again methanol we have launched. This burner was tested at the LPG LERC, which is the authorization center which can test the thermal efficiency. You can see here the conventional burner, the ideal efficiency of the conventional burner is about 45%, and we got about 62.5%. This was certified by LERC. Then we have done many such the cases, and for example the temple they have given up to about 40% savings, and IIT Tirupati, it's been in operation for all the messes. It's been in operation where we got the savings up to about 70% some cases. And against the best performing Korean burner, we got the savings about 37%. So this is again, and you can see here this is a small thing. These are the installation happened at IIT Tirupati, and so again so many things. And just to have some numbers. For example, for preparing about 60 kg of this is with rice. It's rice with the 240 liters of water. The conventional burner consume about 5.2 kg of LPG, whereas ours is only 3 kg. And you can see the time. Time also there is a considerable reduction in the time. And similarly for the several menus and this been we have tested for more than 6 months. We got the consistent this operation. So now coming to the burner, because the designing of such burners, it's not so easy since it's a ceramic. So if you are not doing the proper thing, then you will end up with having flashback and fire blow up. So particularly the porosity and the thickness, everything need to be carefully designed. We have done the extensive thermal modeling with the help of the thermal modeling, the porosity and diameter, even the mixing tube, the nozzle and everything is finalized. And nearly about 7 PhD students are working, 4 are already graduate now, currently 3 are working. And in fact, this got several recognition. We have about 10 granted patents and few are in the pipelines. And so many publications also we have, of course, came out of this one. So this is our institute. Our institute also received several recognition for its sustainable construction and water conservation. All this is what we are seeing. This is a couple of lakes. It stores nearly about 8 crore liters of water, which will feed nearly about 4 months of our water requirement. So this is our campus. So I think hope I have.
I will be covering some of the developmental activities we have done in our division and in our group towards fast breeder reactors. So the outline of my presentation is nuclear power program, the introduction, role of fast breeder reactors, development of components. We develop components, process and systems, and some particular sodium instrumentation and sodium therapy systems. I will be running over these things. So because of an indigenous technology and new type of technology for fast breeder reactors with sodium coolant, a lot of systems and equipments we need to develop indigenously without any help from outside countries, with minimum help from outside countries. So a lot of things we develop that will be explained in a short. So this is the 3-stage nuclear program of the country. The first stage will be with uranium-235, uranium-235, and then to plutonium-239, and then with uranium-233. The second stage, we are in the fast breeder reactors. We are utilizing plutonium-239, which converts uranium-238 to plutonium-239, and in addition to that one, it will be converting thorium to uranium-233 also. So this is the status of the power plants in India. And the fast breeder reactor is FBR is under commissioning stage. It is fuel loading is started, and it will be expected to come critical by March or April of this year. And the role of fast breeder reactors is one which produce more fissile material than it consumes. and the fuel of first order reactors is plutonium oxide or uranium oxide mixture, plutonium oxide and uranium oxide mixture, that is the standard fuel. And liquid sodium is the coolant, all large first order reactors, liquid sodium is the coolant which required special technology and special safety features to use liquid sodium as the coolant in the same manner. And the thermal efficiency of the reactor is around 40%, and this gives high low specific radiation waste generation, and high burn up of the fuel, plutonium oxide and uranium oxide fuels gives low recycling cost, and it can burn out the high radioactive waste generated by the first stage nuclear reactors, which will reduce the storage requirement of the spent fuel. So these are the few equipments we developed. These are the heat transfer equipments we developed. That is sodium to sodium intermediate heat exchanger and steam generator. One side, shell side, it will be flowing sodium. Steam side, it will be steam or water at very high pressure or 173 bar pressure. And other decay heat exchangers, sodium to sodium decay heat exchangers, and sodium to air heat exchangers, which is also both the last two things are for removing the decay heat from the reactor systems. So these equipments we made prototype in the first, tested extensively, given the feedback to the actual equipments, and that is implemented, and then we manufacture this equipment and implement in the reactor. So many fundamental phenomena we could find it out and we can solve these things. I am not going into the details of the thing. And then the second series of equipments what we did is development of valves. And for basically the present reactor, almost all these valves were imported from the European Union. So after that one we started an extensive program to develop sodium valves in our country. So we developed all the types of valves required for the hospital reactors, which is liquid sodium applications, and which is highly cost effective. And many of the things, for example, the frozen seal butterfly valve, the one valve was costing around 80 lakhs rupees at, in around 2009-10 time, and around 2015 time we manufactured this valve in India for 70 lakhs rupees. So all these valves, this order of saving is this much, and we could now the supply chain is established in the country. So this is a huge work, different type of valves, different phenomena. That is frozen seal valves, mellow seal valves, non-return valves, needle valves. All these valves we developed, and a lot of experimentation has gone into this one. And another equipment, then the future reactors, we are looking for passive shutdown systems, which is when the sodium coolant flow is reducing, the shutdown system will activate automatically because of the pressure drop will increase. The buoyancy force will overcome the drag force, and the controller will fall automatically. This hydraulically suspended absorber rods, it's called HSAR. We developed this HSAR equipment, this shutdown system we developed. We designed the things, we tested it in water. Sodium testing is going on. So in the next reactors, we will be implementing this hydraulically suspended absorber rod. So the loss of flow excellence can be eliminated with this system. And another major problem in sodium reactors is the gas entrainment. It's a pool type reactor. In large pool with high velocities, in the surface velocities, gas entrainment is a major issue that can give operational difficulties as well as reactivity fluctuations. So to mitigate this gas entrainment, we developed gas entrainment mitigation devices. Basically, it is reducing the cross flow velocities. So baffles we designed, we tested it in 5/8 scale model, and we ensured its performance, and this we implemented in the present reactor itself. And another major equipment what we designed is a surge tank. Basically, sodium in the sodium cooled first order reactors, there is a possibility of sodium water reactions in steam generator.
And in case of sodium water reactors, large pressure surges it has to be absorbed. So typically a such tank we are providing the secondary sodium system of the reactor system. So, but it was introducing slightly large pressure drop, and it is in the order of around 0.7 bar pressure drop was inducing in the such tank. So that we addressed, and we tested, we redesigned the such tank, and we could reduce the pressure drop by around 48%. And the height required for the gas and mitigation was also reduced by 37% with this conical type of porous shells, which reduced the duty of secondary sodium pump by 4.8%. It's a sustained gain of 4.8% duty in the secondary sodium pump. And another flow issue was, another thing was we developed the flow zoning device for the fuel sub-assemblies and other special sub-assemblies and blanket sub-assemblies. And without cavitation, we have to, for equal flow zoning, it was required to drop between 0 to around 37 meters of sodium column without any cavitation. So, stacked honeycomb type of orifices we developed. And the another challenge was to manufacture this. We developed these things, and then when it was manufacturing in NFC, and the inspection of these, pressure drop devices in an accurate manner was it was a challenge. Then we developed a visual-based inspection system to inspect the things automatically. With the vision measurement system within 2-3 minutes. So this required hundreds of orifices in a core. So thousands of orifices in a core. So the inspection was a challenge. Each and everything inspecting was a challenge. So we made an automatic inspection device also for this. Then another area was we developed a few process towards the hospital reactor program. The cold trap, which is purifying, of course, this we did that in collaboration with ICT. Professor Pandit sir was collaborating with us. The cold trap, which is purifying sodium, will be saturated within 4 to 5 years because of trapping the hydrogen diffusing through the steam generator valve will react with sodium, and it will form sodium hydrate, and that has to be trapped by cold trap. So it will get saturated. So every 4 years you have to regenerate these cold traps. The cold trap is a big equipment. It's around 2.6 meter diameter and around 5 meter height. So it has to be regenerated every 4 years. So we developed a process for regenerating this cold trap and make it new after every 4 years. And further, the sodium manufactured in India, the sodium for QFBR was imported from France. The sodium manufactured in India was with higher carbon content. So we have to reduce this carbon to around 6 ppm, and the carbon content was around 60 ppm. So we made a process to remove the carbon from sodium. So first we characterize the carbon particle size. The solubility of carbon in sodium is around 2 ppm only. So rest of the carbon is in the form of crystals. So we characterized the carbon particle size in sodium with the help of our metallurgy group, and then we designed the proper filters to remove carbon, and we implemented that things, and we could reduce up to 14-15 ppm. And further we employed a hot trapping process here as a spot material which absorbed carbon, and we could reduce to 6 ppm levels. It was very successful project. And now we can, whatever carbon content, industrial sodium which is produced in India can be converted into nuclear grade sodium. And we developed many other systems also. For removing the decay removal, we characterized the decay removal systems, and we did extensive experiments with the decay removal systems. In PFBR, there are 4 decay removal systems, 2 different types of 4 into 8 megawatt, the 2 megawatt decay removal systems are there, which remove the heat from the hot sodium and eject to atmospheric air. So this system, the complete characterization of the system we did, and feedbacks were implemented in the system, and it is now during the commissioning stage, the system is working perfectly. And another thing was, in future reactors, now the primary sodium of the reactor is purified with the purification circuit called RAP. We are taking the sodium, primary radioactive sodium outside the reactor vessel and then purifying and sending back. We are thinking of implementing in-vessel purification system, which will not take the sodium outside. But the problem is here the cold point of the cold trap is 110 degrees centigrade, which has to be generated in the hot pool of 550 degrees centigrade. So we have to make an equipment maybe around maximum 800 mm diameter, 600 to 800 mm diameter, where we have to generate 110 degrees centigrade in a sodium hot pool of 600 degrees centigrade, where sodium is highly conductive. So sodium conductivity is around 76 parts per meter Kelvin, and in that conductivity range we have to generate. With the multiple cooling circuits and economizer circuits, we could make this equipment. We demonstrated, we designed, manufactured, and demonstrated the functioning of this integrated cold trap, and we could purify around 20 tons of sodium repeatedly. And then further, plugging indicator is another equipment which measures the purity of sodium, and the purity of sodium is measured by its impurities in the sodium will be precipitating with respect to temperature. We cool the sodium, and the impurities will precipitate in small orifices that will restrict the flow, and flow reduction will give indication that the flow reduction will give the indication of the impurity of sodium, impurity level of impurity in sodium. This is basically depending upon many other parameters, the rate of cooling, the plugging indicator design, the operator, the interpretation of the things. So we made these things into automated things, and we are in the process of using AI for this system. So we can repeatedly we can use this, repeatedly we can sample sodium in a day. Now it is it was a tedious process of 6-7 hours of operation. So we have large amount of operating data. So by using that one, we automated this system, and we are planning to use the AI tools for automating this indicator, plug indicator. Another system is the steam generator leak detection system. As I told, there is a possibility of sodium water reaction in steam generators. The steam generators, the sodium water is leaking to steam, the sodium it will react, and hydrogen will be produced. So the presence of hydrogen we have to measure. The presence of hydrogen is the indication of tube breach in steam generator. So we developed a system to detect hydrogen in sodium through a nickel diffuser, and hydrogen will be diffused through the nickel diffuser, and a sputtering pump will evacuate the hydrogen. The current of sputtering pump will be the measure of hydrogen in sodium. That can give a higher current in sputtering pump, indicates a higher hydrogen concentration in sodium. That can initiate safety actions. And then these are some of the equipments we did for sodium flow and pressure measurements. These are all first of this kind in the sodium pressure measurement. There is no conventional device to measure sodium pressure and sodium flow. Also, permanent magnet flow meters are used for sodium flow measurements. And the bypass permanent magnet flow meter we developed. And to address the industrial safety related to sodium, we developed numerous equipments like resistance like plugging indicator, sodium aerosol detectors, and finally we are using vision-based smoke detectors, which is using AI. So it can distinguish with camera, we can capture the frames, and unlacing that one we can detect sodium fire in a very perfect manner. So smoke will be any sodium fire which will react with oxygen, and the smoke will be generated. The smoke will be detected, or the flame will be detected. So very efficient incipient of sodium fire can be detected in the plant. So it will be, these systems will add a huge way to the industrial safety of the nuclear reactor. The summary is hospital reactors with cross-fuel cycle has a large potential to meet the future energy requirement of India. India has pursued a path of self-reliance with limited international cooperation to develop hospital reactor technology in the country. Towards this goal, equipment, process, and systems were developed indigenously. Some of these developments works are first of this kind, and other That's the first of this kind in the country, all the works. And this development program gives remote dependency of components and technology for a capital.
So as a country, India as a country, we have put up this ambitious target of achieving 5 million tons of hydrogen. So as a country, we have put up this ambitious target of achieving 5 MMTP of green hydrogen of production as well as consumption or export by 2030. And what do you mean by green hydrogen is essentially that we will electrolyze the water using renewable electricity and then store that hydrogen and use it as and when required for various applications. Now when we are talking about 5 MMTP of green hydrogen, we essentially need roughly of the order of 100 gigawatts of RE, 50 gigawatts of electrolyzer plants, 2000 tons of hydrogen storage, and the downstream applications, refineries and fertilizers and steel we already have. But we still lack fuel cells infrastructure. So in this context, and to build all of this, we will need roughly of the order of $100 billion of investment over till 2030. In this context, I will present with two examples how modeling and simulations can help in achieving this mammoth target. I will first start with PEM fuel cells. It's the downstream part of hydrogen economy where this device converts hydrogen back into electricity. And these fuel cells find applications in various markets such as stationary backup power as well as mobility sectors. However, deep penetration of these devices into the markets has still not happened. And the major barrier for this is its current high capital cost. Now, one of the ways by which the capital cost can be lowered is by increasing the power output of this device. However, identifying precise scientific innovations which can help increase the power output of a fuel cell, finding such innovations is not trivial. And it becomes even more challenging because there is no simple correlation that relates electrical power output of a fuel cell with its parametric space, which is what I have solved and I will try to cover in this particular couple of slides. So this device is essentially you have hydrogen flowing through this anode side and hydrogen splits into protons and electrons. Protons migrate through this membrane and reach the cathode side of the fuel cell and the electrons flow through the external circuit. On the cathode side you have oxygen flowing through the channels and it simultaneously diffuses and reaches cathode side. So on the cathode side we have oxygen diffused from flow channels and gas diffusion there. We have electrons from external circuit and protons migrated from the catalyst, from the membrane. So all of these combine to form water. And it is found that the anode side reaction is 10 to the power 5 or 6 times faster than the cathode side intrinsic kinetics. However, the intrinsic kinetics on the cathode side may get hampered by the slower transport processes of proton flux and the oxygen transport. So we first recognize that this is a classic chemical engineering problem where you have chemical kinetics that is happening in the catalyst layer and it gets hampered by either slower oxygen transport or slower proton transport. The only complication here is that one of the reactants is entering from this side and one of the reactants is entering from the other side. And of course the governing transport processes and therefore the governing equations are a little bit involved. However, we find, we first of all solve these equations using series solutions and we find the oxygen concentration profile and the proton flux profiles in the catalyst layer. And we find that when you have oxygen transport being slower, then the reaction fronts moves towards the oxygen radial interface, which is again standard chemical engineering principle. And when the proton transport is slower, the reaction front moves towards the membrane catalyst interface, again because it is the slower process. And because we could figure out the concentration and profiles of concentration as well as current densities,
we can then correlate it to find the voltage current relationship or the electrical power output just based on this one-dimensional framework. We then use this one-dimensional framework and extended it to two-dimensional or the full cell, so to speak, wherein we have the oxygen that is flowing in the flow channel while it is simultaneously getting diffused in the gas diffusion layer, and the catalyst layer reaction kinetics affected by transport processes we have already figured out. So we solve this transport equation with this boundary condition where the oxygen consumption rate in the catalyst process is already defined from the one-dimensional framework. So once we use series solution to solve these equations using these boundary conditions, and we figure out the concentration profiles and current density profiles in various domains. We use all of this to eventually get the what we call voltage current curve, and surprisingly it forms a very nice closed analytical form. We validate this the outcomes of this equation using full-scale three-dimensional multiphysics simulations as well as with experiments, and we find that we have a good overlap of the analytical solutions with 3D simulations with the experimental data. The beauty of this equation is that you can now use this in Excel, and you can run this Excel 1,000 times, 10,000 times, 1 lakh times, however times you want, and then you can come up with, if you may want, the simple correlation between electrical power output and all the parameters that are involved. The other beautiful thing here is that in standard chemical engineering practices, there are always length scales, time scales that drive the various outcomes of various reactors and so on and so forth. Here we could figure out that those time scales or length scales are transformed into what we call current density scales. The fundamental processes remain similar, but the scales are in terms of current densities. So with this, I'll jump to the second example, where the problem statement is that we want to produce the final green chemical, which may be green ammonia or methanol, at the lowest cost. And you have to begin with the COF profiles that are given to you for 8760 hours over the year. Now, what is the optimum sizing of all these plants, starting from RE power to BESS, to electrolyzer plant, to hydrogen storage, and the downstream ammonia and methanol plants, such that you get the required output, let's say 1 million tons of ammonia or 1 million tons of e-methanol, but by minimizing the total installed capex. Now, why do you need mathematical optimization here is, I will explain in 2 or 3 points. First is, if in a traditional process plant, one always tries to run the ammonia plant or methanol plant at 100% CUF, or let's say 110% CUF. But here, what that means is you need to have a very, very large storage because of monsoon fluctuations and so on and so forth. So in this particular case, it may be possible that if you run your process plant at little lower CUF, and you can minimize the hydrogen storage size such that your total capex can be lower, and while operating your process plant at CUF lower than 100%. The other aspect here is that you may want to increase, you may want to oversize the RE plant with respect to electrolyzer plant, such that some of the energy you want to curtail, but that increases the CUF, the capacity utilization factor of electrolyzer plant. So therefore, again, the combined capex can be lower for a given throughput of hydrogen. So the problem statement here, the mathematical optimization, is that you have all the variables being the sizes of each plant. The constraints are the technological constraints, such that the ramp rate, the minimum load of the electrolyzer plant, minimum load of the ammonia and methanol plant, ramp rates of ammonia/methanol plants, and the objective function is capex minimization. So one of the typical results that there are lots of results that we have figured out, but one of the results that I have found is that let's say in this particular time window of the year, you have a battery that is degraded as in battery doesn't have enough state of charge in it. Correspondingly, the optimization has told us that you may want to run your ammonia plant. This black line is the ammonia operational load. The ammonia plant you may have to run at lower loads rather than at 100% load. Whereas this ramp rate is matched. It's given by the OEM. You cannot increase the ramp rate by X% per hour or something like that. So such kinds of insights we gather, and this framework is being used right now to figure out the total sizing of various plants to minimize the capex of for producing the green chemicals. So with this, I will stop here. So I've been working on a separate area called antifreeze proteins, which I will not be able to cover today. So I'm sorry. Thank you.
The topic of my presentation is reconfiguring multi-port converters for multi-voltage electric vehicle charging. And I am an assistant professor at Indian Institute of Science. I joined IISc in 2020. So before that, I did my PhD from North Carolina State University, and I worked with GE Research both in India and Bangalore for some time. So this work is primarily based on what I've been doing at IISc for the last 5 years. So if you look at the Indian EV ecosystem, the current scenario is we are selling roughly around 2 lakh vehicles per year. And if you look at the charging scenario, in this cartoon we see that we have around one public charger for 135 EVs. If you look at China, they have one charger for every 6 electric vehicles. And if you look at US, they have one charger for 19 electric vehicles. So we are kind of lagging behind in terms of the charging infrastructure, and this can become a crucial factor when it comes to EV adoption. And India has very ambitious goals in terms of EV adoption. So if you look at our scenario, currently our EV segment is fragmented. We'll see what that is in a minute. And we have non-standard batteries specifically for 2-wheelers and 3-wheelers. Public charging infrastructure is yet to catch up. And we rely heavily on imported technology for chargers. And again, when we are thinking of huge EV charging infrastructure deployment, it is going to put quite a bit of stress on the existing grid. And again, we have national visions like Bharat, NetZero 2070. All of this can be achieved only with indigenous technology development, and we have to go quite a long way. And we have been specifically looking at next generation charging infrastructures, where we are trying to look at indigenous and innovative technologies for charging systems. And I'm also looking into, let's say, solutions from an electronics point of view in terms of the EV battery and safety. I'll talk about the charging systems for this talk. So if you look at the 2-wheeler segment in India, we see that again the batteries are not standardized. The standard says that for 2-wheelers and 3-wheelers the voltage should be below 125 volts, and we have quite a wide, let's say, range of voltage. I mean, we have batteries with 48 volt nominal voltage, 60 volt nominal voltage, 71 volt nominal voltage, and there's quite a bit of variability among the batteries which are provided by different manufacturers, and this is not going to change. Because the battery technology in itself can be a differentiating factor for many companies, and again the voltage level, because it is well within the standards, and the standards are very loose, at least in the 2-wheeler, 3-wheeler space, there's quite a bit of variability. And same with 3-wheelers, most of the solutions that are there are 48 to 60 volts. The older generation electric cars, we had 48 volt for Mahindra, Reva, the first generation cars and all, but the latest cars, I mean, there the standards have become established, and we have around 400 volt nominal batteries for electric cars. But there's a tendency to move towards 800 volt systems for fast charging and things like that. So at least the 2-wheeler and 3-wheeler space, there's a lack of standardization, and there's a lack of public charging infrastructure. The problem is we have different types of batteries. So how can we build a public charging infrastructure What we have now is different companies. I mean, they are putting up charging stations with their proprietary technology, which may cater only to their class of vehicles. So I cannot take my, let's say, scooter to any public charging station. For example, if I have an Ather scooter, I have to take it to an Ather charging station. Likewise, Ather, Ola, a couple of these players are setting up charging infrastructure. And again, these are fragmented efforts, and we cannot have a public charging infrastructure where any scooter can be charged in any station. And these need not be big deployments. This can be deployments in office spaces. This can be deployments, let's say, in supermarkets and things like that. And even let's say in home, let's say if, typically in our homes we'll have 2 to 3 two-wheelers and a four-wheeler. So every two-wheeler will come with its own proprietary charger, which will be used for charging. And even modern, let's say, apartment complexes that are coming up, everybody is just connecting their own proprietary charger. And at least for four-wheeler, there is an effort towards building a common charging station when the apartment complex comes up. But for two-wheelers, that is still not possible because of these issues. And the same with swapping. For two-wheelers, there is again a big debate between charging and swapping. So there are a lot of proponents for battery swapping. The challenge again is similar. For example, in Karnataka, Honda is setting up several swapping stations in and around Bangalore. But again, you cannot store 10 different types of batteries in a swapping station. So again, you will have a swapping station where a particular type of batteries will be stored. And then again, that puts in a bit of a limitation or a challenge. So both these situations, even in a swapping station, the batteries that are getting swapped will have to be charged. So there has to be some charging solution in a swapping station as well. And the brute force, let's say if we are thinking of a democratized charging scenario where we can go to any charging station or swapping station, we need to have some kind of, let's say, universality in charging. And the brute force solution is to install multiple chargers which can cater to 48 volt batteries, 60 volt batteries, 72 volt batteries. But again, that can add a lot in terms of the cost and complicate the infrastructure. So our aim, at least one of the technologies that we have been developing is a universal charger which can cater to a wide range of voltages. So you can charge any battery irrespective of the manufacturer, the battery type and things like that. So this is one solution that we have developed in the laboratory. One of my PhD students is leading this effort. So this is a multi-port charger where we have a grid connected, power factor connected front end, a multi-port front end. Again, this is a soft switch converter. And then since this is low power charging, we are looking at unidirectional solutions. And we have diode bridges in the secondary. Because we have diode bridges in the secondary, the output voltages cannot be regulated precisely. So we have a post-regulator converter. And this post-regulator, what it can do is it can regulate the output voltages precisely to meet the requirements of the battery. So and this voltage can be varied over a wide range from 40 volts to 100 volts so that any battery can be connected. And this is the charger that we have developed, the initial version, and then it has been packaged. So we have been able to take this to TRL, let's say 6, where we have done the field demonstrations. And for example, here we are actually testing this charger with real scooter batteries. And these are batteries from 3 different manufacturers. One is from the battery which is used in kinetic scooter, another is from Hero, and the other is from Okinawa. And we are showing that with the same charger, we can charge 3 batteries. So we have connected 1 battery to each port. We can charge 3 batteries simultaneously, and these batteries can be of different specifications. And then again, these are some test results. So from the grid, we are able to draw, let's say, sinusoidal currents, near sinusoidal currents. And if you look at again commercial solutions, many of the commercial solutions which are imported from China, they use a diode bridge based front end. There is no power factor correction because the power level is too low, it doesn't fall under regulation. So we have compared this with a commercial charger, and the commercial chargers draws very peaky currents. And again, setting up an infrastructure, if you want to set up an infrastructure and charge 10 scooters or 20 scooters, we cannot buy such solutions and put together this kind of an infrastructure. And we are going to again draw non-sinusoidal currents from the grid. But this kind of a solution, it's scalable. Even for higher powers, at least we will not have power quality problems. And again, you can see the 3 different batteries getting charged simultaneously. So we have further extended this idea. So one is, how can we scale this? So previously what we showed was a single phase, solution. So I can make this phase modular so that I can connect it to a three-phase grid for higher power applications. And then what we have done is we have tried to make this reconfigurable. So I can now charge either 3 scooters at lower voltages. Each port can operate from, let's say, 40 to 85. Or I can series connect the different ports and I can get a higher voltage port. So I cannot operate all 4 simultaneously. I can either operate 3 low voltage ports or one, let's say 250 to 450 volt port, which is compatible with the car battery. So I can either charge 2-wheelers, 3-wheelers, or multiple 2-wheelers or 3-wheelers simultaneously, or I can charge one car. And let's say for 2-wheelers or 3-wheelers, I mean, we can go up to 3.3 kilowatt, which is currently on the higher side. The commercial 2-wheeler, let's say chargers are typically the maximum power is around 800 watts to 1 kilowatt. Mostly the, let's say, everyday scooters and all, the battery, I mean, the charger ratings are like 300 watts to 500 watts. But we can go up to 3.3 kilowatts, which could be considered as even a fast charger for scooters. And 10 kilowatt for charging. 10 kilowatt is again on the lower side for car charging. So nowadays, people are talking about at least 20 kilowatts and things like that. Again, this is a technology, it can be scaled, but this is very suitable for home charging, let's say at night or something like that. So we can charge 3 scooters or let's say 1 car with this technology. And again, this was built from the scratch. Every board that you see here has been built by the students in the laboratory. And we have packaged it and again we have tested it, and you can see that it this is a condition where it is drawing 10 kilowatt from the grid. Some of the outcomes. So again, this was done as a part of an interview project thanks to DST, and we demonstrated this in the field, and we were charging real scooters, multiple real scooters using this charger, and this was demonstrated to the National Scientific Advisory Committee in 2023. And this is the student Himanshu who has been instrumental in developing this. Several other project associates and tech students worked on this. So this technology was selected as a cutting edge technology by DST. I mean, the projects which they have funded, out of which they have selected a few technologies for exhibition in Vigyan Bhavan during the environmental day this year. And the student is a PMRF student, so he received the best poster in the electrical engineering category for this work. Again, he received the Gandhian Young Technology Innovation Award for this work. So, some of the other students, what they have been looking at is again, the primary technology is multi-port converters. So in multi-port converters, again, rather than using it for charging multiple vehicles, we could also use it to interface, let's say, solar and storage. Again, somebody pointed out that these kind of charging infrastructures are going to put a huge load on the grid. So it is better to make it self-sufficient where we can integrate, let's say, renewable energy, and also that will make it a bit more greener rather than, let's say, using electricity which may be generated using coal to charge an electric car. We could use renewable electricity to charge cars. So we could interface solar storage and such technologies also using these kind of multi-port converters. So that is another applicability. And we are extending. Previously we looked at unidirectional converters for charging. Here we are kind of making it omnidirectional. I can transfer power from any port to any port. And again, this work has been recognized internationally. One of my students received an IEEE Transactions Prize Paper Award for this work. And for both these, I mean, we have submitted patent applications. One patent has been granted, and the student has also received a couple of other awards from IISc and also the national level. So in conclusion, we have developed reconfigurable chargers which can be used for charging multiple voltage classes and even potentially multiple segments of vehicles. And the idea is to democratize charging to some extent. I mean, rather than having individual charging stations for catering to a specific or proprietary type of vehicle, can we kind of open it up, which will be very helpful for the customer, because it can be like the petrol pumps. I don't need to care about whether I go to an Indian oil pump or a Bharat petroleum pump. I can fill up the petrol, and likewise, I mean, I can go to any charging station without worrying about, let's say, which vehicle I have. So that is the idea behind this kind of universal chargers, and it can also reduce the cost in the sense that, I mean, in terms of components, right? Imagine if I have to build 10 different types of chargers, but now if I can have a universal charger and if you scale it up in terms of volumes, even in terms of the component cost and all, you can get considerable savings. And it can reduce the capital and operational cost, because you don't need to buy 10 different types of chargers. It can be a single, again, this is an idea. There can be variants for this, but again, this is an idea towards how you can democratize charging. And then potentially unless we speed up in terms of EV charging infrastructure deployment, it can help improve the user confidence and accelerate EV adoption. And let's say this can also help India achieve some sustainability goals. And the present technologies are potentially scalable. You can scale it to even higher powers to cater to megawatt charging. Multi-port technologies and integration, solar storage, whatever we are investigating are potentially scalable, and we are currently working towards higher power development and higher power versions of these. So thank you.
Dr. Ranjit, Assistant Professor in the Department of Chemical Engineering, IIT Tirupati. A lot of interesting topic today on energy production, energy transmission. The last lecture today will be on energy storage. So I will talk about the ongoing research, what we do, next generation sodium ion based energy storage system with high energy density. The word high energy density is very important here because the particular thing what we are doing should compete with the commercial state of the art lithium ion battery. So looking into the need for battery really forms an integral part of our everyday's life. Everything is powered by, from a small scale portable devices what I have in my hand to in your hand, mobile phones or laptops, to large scale applications like electric vehicles or advanced applications like drone or green energy storage systems are actually powered by batteries. So looking into the next generation battery, there are 5 most important critical parameters that has to be fulfilled to make the battery as a next generation energy storage battery. The 5 important parameters are high energy density, high power density, low energy, low cost and high safety, and it should be environmentally friendly. The demand for high energy density batteries are increasing day by day. Why this high energy density batteries are needed? So I can say in a very short word. So if the energy density is very high, I can able to accommodate the battery in a smaller space, and I can drive my electric vehicle for a longer range. So this is a very short schematic on how lithium ion batteries work. So I'll start with the lithium ion battery. So it has a cathode, a lithium ion containing transition metal oxide. At least this is the state of the art commercial lithium ion battery. And it has a anode, and when you charge and discharge the battery, the lithium ion batteries shuttle back and forth between the anode and cathode. So these 3 brilliant minds, Professor Goodenough and Dr. Stanley and Dr. Akira Ishino, are a brilliant mind behind the invention of the lithium ion, commercial lithium ion battery. So it's not a single man's invention, it's a combination of the science behind these 3 people, and these are the schematic of 3 lithium ion batteries developed by these 3 people. Okay, so what you really find here is Whittingham, he said that lithium ion can move between anode and cathode. That was his invention. He said that lithium ion can shuttle between the positive and negative electrode, while Goodenough, he found that he developed some commercially available lithium containing transition metal oxide, while Yoshino, he used petroleum coke or graphite as anode, combined the science behind Goodenough or Whittingham to make the first commercial cell from Sony. So although Whittingham developed, so this was his first, this was the first commercial cell. Lithium ion battery has a metallic lithium as anode. The commercial cells what we have it uses graphite as anode, but the first cell by Whittingham, it uses lithium metal as anode, and cathode obviously some titanium disulfide. So this is the first commercial cell developed by him when he was working in ExxonMobil, a petroleum company. So the failure for his battery is mainly the safety. So what really happened is, like, the battery, when you keep on cycling, within few tens of cycles, the lithium metal, rather than moving between the anode and cathode, it started to form a needle-like structure over the anode, and the anode and cathode got short-circuited internally, thereby leading to an explosion. So this is the failure for the first lithium-ion battery. And why this is actually happening is, he directly used a lithium-ion battery, a highly reactive metal with electrolyte. That's its weakness. Although it's a highly reactive metal, it's actually the strength for the lithium-ion battery, because it moves the lithium-ion moving between the anode and cathode. That's the strength, but its strength is its weakness. The lithium is highly reactive with any electrolyte, thereby it causes this series of issues. This is although they tried to overcome the issues, safety issues by developing some lithium aluminum alloy, it didn't really get succeed because there was actually a sudden drop in petroleum prices during late 1980s, which made them to stop using the lithium metal as an anode in his battery. And looking into the failure mechanism in the modern rechargeable battery, what we have in our mobile phones or in our laptops, obviously what we have is a graphite anode and a lithium cobalt oxide cathode. Even in this case, rather than a lithium ion moving itself between an anode and cathode, it started to deposit over the ions started to deposit over the anode as a lithium metal. So this is a inside view of lithium ion batteries after a few hundred cycles. What you observe here is the lithium, it is supposed to move as an ion between the anode and cathode, but it really do not go that way. What you find here is the lithium get converted into, ions get converted into a lithium metal, get deposited over one of your electrode, thereby making an internal short circuit inside your battery. Even with the modern rechargeable battery, the failure mode of failure is actually a internal short circuit mainly by the dendrites. And why these dendrites are happening is due to improper SCA layer formation. I will not go deep into the science, but the understanding is the naturally formed SCA layer. The moment when you fabricate the battery, like there is actually a formation of a native layer inside the battery, so that it will help the battery to run longer. So the naturally formed SCA layer is not as smooth, so it needs a sophisticated technique to make it more smoother and thinner, but this is not happening in any battery. That's why the failure of the battery is happening. So now like I will partially deviate from my previous slide. So metal anode. So most of my work is going to be on this metal anode. So this metal anode in particular is actually called as a holy grail for any energy storage system. So I have given a energy density of value of around 500 watt-hour per kilogram. So this is the target set by Department of Energy US. The major target is to develop a battery technology which has energy density of value 500 watt-hour per kilogram. And people obviously like a couple of years back, they decided that with conventional anodes, graphites, achieving that energy density is practically not possible. So they suggested that moving from graphite based metal anodes to lithium based anode, so move back to a system which we used 30 or 40 years back. So moving to that system will really help us to achieve energy density of around 500 watt-hour per kilogram. That was their final observation. And why this is happening is like when you move from graphite to lithium anode, you can obviously see the theoretical capacity of the lithium metal is actually 10 times higher than the graphite. Per gram of material, you can be able to store at least 10 times higher energy than graphite. Obviously, lithium being the lightest element in your periodic table, you will be able to realize the smallest or lightest battery that can power any electric vehicles or energy storage devices. But as I said, the problem here is the reactivity. So you can see here conventional lithium metal, it can able to severely form dendrites than modern rechargeable batteries. So I am now moving towards the current topic, sodium. So using the knowledge what we gained from lithium, we would like to leverage the knowledge what we have from lithium. We will be using it on sodium. So why sodium? So actually sodium is actually a twin sister of lithium. So being in a periodic table, being an alkali metal, the much similar properties like lithium. So leveraging the knowledge what we have gained from lithium, when we utilize the same knowledge for sodium, we can nicely able to develop a sodium based energy storage technology. Why? Because lithium is one of the rarest metal in the earth crust. So a lot of supply chain issues, which is much familiar case study these days. So Government of India that's also emphasizing that we should develop a battery technology with minerals that's abundantly available in India. So sodium being abundantly available in world, so one can able to develop a technology without any supply chain issues, and definitely it's a really a motivating factor, and it can really provide a nice potential or energy density for the cost. Okay, so there are different types of sodium-ion battery technology. So this is a conventional sodium-ion battery technology where sodium ion moves between anode and cathode. So they generally have carbon-based cathode. So the idea is to replace the carbon-based cathodes with metals, sodium metals directly, so that you can able to develop a high energy density sodium-ion battery technology with energy density nearly equivalent to lithium-ion battery or much higher than lithium-ion battery technology. But however, as I said, lithium-ion metals has a lot of issues, in particular dendrite issue. Why this dendrites are happening is due to poor interface stability between the electrolyte and metal. So our research group has tried to stabilize the lithium metal by developing a sodium ion conducting alloy layers over the sodium metal. So rather than making the SEA layer to form naturally over the sodium metal, we have grown it artificially over the sodium metal. So the first thing is we try to stabilize the lithium metal by developing a alloy layer. So we realized that this will really push the energy density of the state-of-the-art sodium-ion battery technology beyond lithium-ion battery technology. So we have developed a series of alloys. So we realized that develop sodium-indium alloy or sodium-bismuth alloy or sodium zinc and sodium tin. Several alloys, like they were grown with a fissile solution-based technology, a simple chemical reaction. You can see there at the last figure, like artificial SEA layer based on these alloys were nicely grown over the metal. And what you observe here is when such artificial SEA layers are not grown, obviously the previous discussion what we have seen, a lot of needle-like structures were grown over the sodium metal, which will penetrate into between the anode and cathode, thereby internally short-circuiting your battery. But however, we really didn't observe such needle-like growth over the sodium once we put the artificial SEA layer over the sodium metal. And the sodium ions can easily diffuse over the artificial SEA layer, nearly works like a naturally formed SEA layer. But however, when we try to cycle the battery at higher current rate, which means when I am fast charging the battery or when I want to develop a large sized battery, this is actually showing an issue. So the first issue we have sorted out that if we come to a conclusion that when we develop an artificial SEA layer over any sodium metal that can nicely function, the battery can undergo charge and discharge without any short circuit. You can observe here the black one, that is with naturally formed SEA layer, but however with artificial SEA layer the batteries can be cycled easily. But however, we really had issues at high current and capacity. When I want to make a battery with high capacity, say for example 150 Ah or 100 Ah, that's really not possible with the solution what we had, or when we want to cycle the battery at higher current density, higher charge rate, that's not possible. So we address the issues by replacing the alloy-based artificial SEA layer with solid electrolyte complexes as a SEA layer. So what we observed is the mechanical strength of the SEA layers, which is grown over the metal anodes, really impacted how fast the battery can be charged or discharged, and it can really impact the size of the battery we have grown. We have successfully studied all the batteries in a coin cell level prototype that the batteries can be even cycled at a current density of around 10 ampere per centimeter square and with a capacity of around 30 mAh per centimeter square efficiently. A significant leap from our previous study. And when we studied a practical cell, it can be a sodium metal based battery or a solid state battery, which are really fireproof or explosion proof. These batteries employing our modified sodium metal anode nicely showed good stability over several hundred cycles when compared to conventional sodium metal anodes without any natural SEA, without artificial SEA layers. Okay, so these are the conclusions from my presentation. Obviously, sodium metal, it really offers high capacity and it's it's a low cost, but obviously natural SCA layer has its problem, and it can be addressed by developing several artificial SCA layers based on alloy type anode or solid electrolyte type SCA layer anodes. So next generation sodium and better based battery can offer really high energy density than state of the art lithium ion battery, but obviously the energy density will be lower than lithium metal battery. So still large scale prototypes are still challenging because utilizing or developing large sized batteries with metal anodes really needs a lot of engineering challenges, which we are trying to address it through the ongoing EV mission, Maha Mission Mode project. So thank you.